Okay, long time no see. Today we'll talk a bit about Hadoop, Spark, and streaming analytics, also related to assignment number 3, which hopefully you've been able to, in the meantime, set up correctly. If not, let me know. I'm also busy collecting the data for the final assignment. In the course of this week, you can also expect the instructions on at least how to set up for that assignment to be posted during this week as well. And then finally, also for the very first assignment, by now you should be kind of finalizing or working on your final submissions and models, because also maybe by next week or in 2 weeks, I will also post like an announcement detailing that. But the submission portal or website will be closed, and the hidden part of the test set will be revealed with the final leaderboard standing, so that you can reflect upon, did we overfit, yes or no, and how do we rank on that final leaderboard. But I will also post a message with regards to that on Toledo later. So for today, we have Hadoop and Spark to go through. Next week will be a session on text mining and a bit on the space of transformers, LLMs, recurrent neural networks as well, a bit. And then in the final week, we basically focus on graph analytics. And that's also what the final assignment will be about. To start with, a bit of in the news. This is maybe interesting with regards to the second assignment. So probably you have been experimenting with convolutional neural networks mainly, or maybe something else, to kind of figure out the location of where a picture was taken. So if you remember, that was what assignment number 2 was all about. Basically, by now, LLMs have gotten so good, if you take a look at ChatGPT's or OpenAI's rather O3 model, that you can basically give it a picture such as this one, and it's deciding, it's analyzing the image, it sees that there is a license plate in there, it decides to run some Python code to zoom in on a part of the image to basically zoom in on the license plate, because it thinks that it can confirm based on this where the picture was taken. Indeed, it seems to follow the standard California design, it analyzes a bit further, and so on. It thinks for, or it reasons for 6 minutes, and then it basically comes up with it either says, well, the immediate backdrop of the image together with where we are. It seems like we are in Cambria in California. So I think you snapped it there. If not, I think my next guess would be the Half Moon Bay, El Granada, a little bit further north. And indeed, the first guess is incorrect, but the second guess is actually the correct one. So, and actually the first guess is not that far off either, only 200 miles. So models are getting quite good also at just based on a picture to see where it was taken. Just wanted to let you know. There is also something quite similar. This is using Gemini. There are like a lot of UNet-based segmentation models out there. There is also Segment Anything from Facebook. Segment Anything 2 is out there. There are like other segmentation models, but also here, these multimodal models that we have gotten good enough that you can basically give it an image and ask it to, please give me the segmentation mask for the pelicans, and I want it as a JSON list of segmentation masks where each entry contains the 2D bounding box in the key box 2D and the segmentation mask in the key mask. And the thing just goes ahead and gives you the reply, and it's close enough, right? You don't need kind of a separate model to do that anymore. So we're going very fast in this space as well. Also thought this was interesting. This is a hobby project, but this is also pretty cool. This is someone recording a walk that they are doing outside in a forest trail with their phone, and they're using like a special app which is also recording the motion that the user is taking, whether the user is looking to the left or to the right. And then they take all these frames and they basically train a model to try to predict the next frame based on the previous 10 frames or so, as well as the motion that has been recorded. And the interesting thing about this is that they're not using like a super fancy sort of diffusion model. You also notice this, that the output is not perfect. They're using a rather standard, the model is a little bit lower, UNet, or rather simple UNet style of model as well. Cost them about $100 to train it, which is corresponding to $100, more or less. And they actually get something out of there which, yeah, it's not super convincing, but it goes to show that you can still do like these kind of fun little projects on your own with like a limited budget. And the links will also be posted as always, but you can play with it yourself once it is loaded and kind of look around. And it's basically, the model is kind of hallucinating, let's say, details in there, and you can walk forward and so on. And yeah, I thought this was pretty cool as well. Next up is I like to play around with 3D printing, and I'm not into like super fancy CAD models to do that. And I thought this was interesting because the tool that I regularly utilize to do this is called OpenSCAD, which basically allows you to define your models through code. And here is someone basically again implementing an MCP server where they can connect this program with a running LLM model, and then just through prompting the LLM model, ask it to generate the code that generates the 3D model. So more and more integration with large language models to several backends provided by these programs or towards several programs is also rapidly increasing. Then the next thing that I thought was pretty interesting is, of course, people are still playing around with coming up with prompts to jailbreak large language models, even although companies try their best to protect models to be jailbroken. In the past, we had seen several users who had gotten pretty good at finding these kind of specially crafted prompts to jailbreak a model. Jailbreaking basically meaning in the sense that you can ask a model how to make a bomb and stuff like that, which normally they would refuse to answer, but to kind of spur them to answer anyway. And this piece of research has basically tried to look whether there exists something like a universal jailbreak prompt that would work pretty well on whatever language model that's currently out there and which is pretty modern, and that would work on all of them without having to craft a specifically set up prompt for each of them separately. And they come up with this prompt, basically with this piece of text, which looks a little bit like some strange form of XML, but is basically specially crafted garbage. And they show that if you indeed dump that into a ChatGPT or something else, normally ChatGPT wouldn't answer with treatments to cure your skin cancer, but after having given this prompt, it's more than happy to give you an answer and to do or to answer to whatever question that you might have. And they kind of execute this on several models that are out there, including 4.0, 4.5, 4.1, 01, 03, Claude 3.5, 3.7, Gemini 1.5, 2.0, 2.5. And the prompt works on all of them, perhaps with some minor adjustments, but indeed there exists something like a universally available prompt to jailbreak these models, which is pretty cool, pretty interesting. They also talk about potential bypasses and so on, so also an interesting piece of work there. This is an article from the Wall Street Journal, but I seem to be paywalled, or I have to fill in a CAPTCHA to make sure that I'm not an AI. But this is basically talking about a job which a couple of years ago was deemed to be like the next hot job of 2023, that of a prompt engineer, and companies were like already putting out vacancies for prompt engineers, and currently this is already dying down because models have become or are becoming so good, and new tools are appearing that these prompt engineers are not necessary anymore. In the US, you could have gotten a salary as a prompt engineer of 200K, so this job is, in this time span of 2 years, this job came and went, basically. Also thought this was pretty interesting. This is an article that was heavily discussed, and this goes into the topic of, does it actually make sense that we perform all these post-training steps of LLMs where we use reinforcement learning, things such as reinforcement learning from human feedback, GRPO, and so on? Does it actually improve reasoning capacity in LLMs beyond the base model or not? And they find some interesting results because well, most of the results seem to suggest that, yes, by performing reinforcement learning, perhaps you make your model more aligned to what users expect in terms of output, but it does not lead to any fundamental improvements in terms of what the intrinsic capabilities of the model already were, starting from the base model. Some people disagree with the findings. Some people think that there is a lot of interesting stuff in there, but it also, in general, this kind of questions the notion of, is post-training heavy reinforcement learning really a solid approach, let's say, towards improving reasoning capabilities of base models, or should we perhaps look for something else? There is also a paper of Facebook which was released and which is pretty interesting, which basically says, well, if you start with an LLM, is it possible basically to have it or to optimize the text that it generates to get a certain desired outcome, for instance, a certain image that you're looking for. And what they're saying is, well, you can actually easily set something up like this. You have a generator, which is just an LLM, and this spits out candidates, which are basically suggested pieces of text that you can utilize to then generate an image from. And then you have a separate score system for which they use some kind of broader model, let's say, of the CLIP model that we saw. And remember, CLIP was a model that is able to give you like the distance between an image and a caption or a piece of text. And they use that to score the candidate set. And then by a process of iterative optimization, they give these scores back to the generator. Basically, they're telling the LLM, okay, you gave me 10 suggestions for text that I can utilize to generate an image with. Here are the same 10 prompts that you gave me, or the 10 pieces of text that you gave me together with a score. Can you now give me 10 better suggestions based on that? And they do this over and over again, and indeed they show that by doing this, they can iteratively improve or steer models towards giving better results. And they, for instance, give here the example of this is kind of the desired picture that they want, and they start with suggested text that says, well, a red car and a white sheep. Well, this is already better, a white sheep and a red car in a stunning natural landscape, and so on and so on. So it's basically the model iteratively by itself kind of coming up with better and better pieces of text to generate images with. So what they basically say is, well, you might only have a model which is capable to generate text, but which is not multimodal yet. Then you might have a separate model which is just there to generate images from text, but it's not really a conversational model. So you have two separate models, an LLM and an image generation model, but that is sufficient. Then if you just have a score or a way to give like scores to these generated pieces of text, through an iterative feedback loop, you can actually basically make that combination of these two models multimodal as well, or a little bit closer at least to multimodal. Which is, I mean, kind of expected in a way, but also nice to see that this actually works in practice. So those are the pieces of news that I wanted to highlight. And then it's time that we get started with taking a closer look at what is Hadoop and what is Spark. You're already a little bit familiar through assignment 3, so not all of this will be kind of new probably, or you will have already stuck your toes into the water already a little bit. The main purpose of this slide stack is basically, well, twofold, a little bit in zooming back into the landscape of big data. So today we will be looking at analyzing large volumes of data or high velocity sources of data. We have already went through a more traditional data science tooling lecture a couple of weeks ago, where we took a look at the normal Python R landscape and so on with notebooks and that sort of stuff, where we had already said like, the assumption there is not that you really work in a distributed setup, but over the years, a lot of these tools have taken some advances that we have made in this realm, in the realm of big data, for instance, working with directed acyclic computing graphs and so on, and learn from them. So today we will kind of make the assumption that we will be looking at tools that are meant to work in a distributed setup. So you're really handling large volumes of data, and you're working with multiple nodes, multiple computers that are in some sort of networked setup. And then the question will be, obviously, on the one hand, how do I distribute data, storage, over a distributed set of machines? And the more important question for us is, how do I distribute compute over a distributed set of machines? And specifically for us, how can we perhaps train models? How can we do analytics in a distributed setup? That will be the end goal where eventually we would like to go towards, because as data scientists, at the end of the day, we would like to train models. If we can do that in a distributed setup with large volumes of data, well, even better, right? So that is where we will go towards. What this slide stack will kind of illustrate is that throughout history, that this took a couple of years and a couple of advances before we got there, right? And Spark is one of the key cornerstones that made this happen, let's say. So you could say there is kind of an era before Spark, more like the Hadoop-centric era, which by now no one would really be willing to utilize it anymore, but so it's more for historical purposes. And then there is an era after Spark that basically had a new perspective on this situation. Not that Spark itself is always easy to use, as you will probably have noticed yourself as well, but at least it made some things possible with regards to analytics in a distributed setup. Also, illustratively, I already used this slide before, right? But again, remember these kind of landscapes that are like growing and growing, very overwhelming, and some are more focused on the analytics side, some are more focused on the storage side, some are call themselves big data, some do not, some talk about infrastructure, what's the difference between analytics and machine learning and so on, and what's all this other applicative stuff around that. So it can be hard to make sense if you see a landscape such as this. But remember, last time we already zoomed in on like the machine learning side, talking about like the Python R ecosystems and so on. So again, we have these two sides. The two most important sides that you will always see contrasted in this kind of overviews is, on the one hand, you have a side that talks heavily about infrastructure. And on that side, you will hear terms being used such as big data, integration, databases, NoSQL, NewSQL, streaming, operations, the ops of ML and the ops of AI. How do you put things in production, monitor them, and so on. Also architecture, etc. You could say that this is basically the plumbing, right? The infrastructure that makes things happen. It's necessary, but it's not really the use case of analytics itself. So that's the other side, that's the analytical side, and there you will hear terms such as data science, machine learning, AI, NLP, still business intelligence and visualization tools as well, for sure. But normally this is the side that we, as data scientists, rather than data engineers, are more concerned with. We would like to do analytics, we would like to get insights, we would like to train models. We have been doing that locally on our own machines. So also there the question will be, how can we lift this up towards a more distributed setting? Now, it might seem that there is a very easy overlap between these two sides, and they can meet somewhere in the middle. The infrastructure provides the, well, infrastructure, and then the analytics can get started and come with the use cases. But that's the whole story here, is that one does not necessarily lead to the other. And at least for, well, let's say a decade or so even, it took quite some time before there was some alignment between these two sides, and there was really an offering that could do both at the same time. Both handle the infrastructure and the storage and the management of large volumes of data, but then also providing sufficient tools, or easy to use at least tools, to perform analytics on that data as well, so to handle the compute side of things. So previously we saw in-memory analytics, where we did already look at some, you could call them intermediate techniques, like Polars and DuckDB and Dask and so on, which utilize smart indexing mechanisms, which utilize disk swapping mechanisms, which utilize directed acyclic graphs, to now being able to offer us more streamlined tools, let's say, that even if you're not working in a distributed setting, are able to handle like relatively large-sized data sets. And I already told you that the excuse that I try to load in a 2 terabyte file into my Pandas and Pandas crashes, that this is now more or less solved. The easy answer would even be like, okay, use DuckDB then and buy a larger hard drive so that you can do some disk swapping, right? A 4 terabyte hard drive is not that expensive anymore. Now still, if you would scale further, if you're thinking on the levels of X.com or Facebook or LinkedIn, of course, then the need to handle even larger volumes of data and to really work in a distributed setting becomes, of course, still more important, and you're not going to handle that with giving all of your data scientists a single machine that they work on anymore, right? Or would be less common, at least. So here we will talk about how do we manage, store, and of course, in the first stage, also query data. Query using maybe some sort of SQL, like in a traditional database, and then also the question, okay, but what will this offer us more than a traditional relational database can, will also be something that we will have to answer, because a traditional relational database is already quite capable to deal with large data sets and is quite good at querying, because since the 1960s, that's what they have been built for. Then also perhaps, okay, but then how can we go a step further beyond querying and also construct models, perhaps in a distributed setting, assuming multiple machines. So that's where we eventually would like to end up. Can we come up with some concept of a distributed data frame, for instance? Or can we come up with a concept of distributed model training? And perhaps even come up with a distributed processing of a streaming data set, a source of events or a source of messages or a source of tweets or whatever that continuously comes in, or a source of messages sent by apps that your customers are using, like your Uber, and you have like millions of users using your app, and that you can in real time perform some sort of event processing or analytics on those messages that you receive, right? So eventually, that is our ending point. But to get there, we will have to go through a series of steps. So we go back many years ago, starting with Hadoop, because for a long time, when you ask questions such as, well, we think that we have big data. A lot of companies in that time that thought that they had big data didn't really have big data. Most of the companies were already using a relational database in which their data was stored, so they spent a lot of money and effort moving that data out into something that they thought would work better, and very often that answer was in that sense Hadoop. So that's still a name that from time to time you will hear being mentioned, and for some amount of time this was the ultimate promise, at least if you didn't know much more about the core workings of Hadoop, in terms of, well, not only can this handle large volumes of data, but if you have unstructured data, well, the answer is also Hadoop, right? You just build a data lake, and you don't need to worry about schemas anymore. Your data can be in raw form, you dump it into your lake, and then later you kind of figure out what you want to do with that data, right? Which is very appealing because you don't need to spend lots of time into setting up extract, load, and transformation pipelines to first process your data in nicely structured formats as if you would have to do, as if you would be building a data warehouse. You could just dump it somewhere and then figure out later what you want to do with it. Because the message was data is the new oil, right? So you better keep it because maybe later it will be helpful. For many organizations, that later never came, and they ended up with data lakes which were filled with garbage, but they never really managed to leverage value out of there. But the answer seemed to be Hadoop at that time. Likewise, if you had streaming data, also the answer was, in that era, was in a lot of cases Hadoop. And even for a data scientist, well, yeah, you're doing machine learning and you want to do that in parallel using all the machines that you have. Maybe you have a cluster of maybe even 10 machines, but still it would be nice that you can train your models in a distributed setting as well. And for a long time, well, also probably Hadoop has something to offer there for you. You can already kind of feel there never exists like a single turnkey solution that can do everything perfectly. So the question is, okay, but then actually what is Hadoop? What did it actually do and what did it not do, right? So that's what we will go through. A lot of people think that Hadoop was developed by Google, which is not completely correct. What is correct is that Google, in 2003 already, so like I said, this is already like from a while ago, published a paper. And they called this paper the Google File System paper. And they were dealing with a particular issue, and they said, well, we have a lot of data, and we are a search company, especially at that time, they were mainly a search company still. Maybe today they're an AI company or an advertisement company or whatever. You know that the US is trying to break Google up into several pieces. But at that time they had an issue. We're crawling the web. We're like collecting all these keywords and we have a lot of data that we need to store. And we would like to store this data in a way which is, yeah, where we can easily add in more machines if we need them or more storage if we need them. So if we run out of storage, we just buy another container and we slot that in and it should just work. So this should be scalable and automatically scalable. And it should also be fault tolerant, of course, because from time to time, these hard drives crash, especially if you have so many of them. So the system should be fault resilient as well. And they came up with a system to handle that. There was nothing out there. The thing that was out there were very expensive solutions where you had to buy expensive mainframes or bulky machines, which they didn't want to do. Their approach was basically, no, we should be able to do this with commodity hardware. Hardware that you just buy, normal PCs basically, normal motherboards, normal CPUs, normal hard drives. And they called this approach the Google File System, a distributed file system. There are other distributed file systems as well. DeepSeek has just released their own distributed file system that they specifically utilize to store training data that they use to train their LLMs with. But at that time, that is what they came up with. Okay, then you have your data, which is stored in a distributed fashion. They published that in a paper. Probably you also want to do some calculations with that data. You also want to perform computations on that data. So they also published another paper called Google MapReduce, in which they explain, here is how you then can do compute with this data, also in a distributed fashion, also on this cluster of machines that you have. And two people, Doug Cutting and Mike Caffarella, were looking at these papers, and they were at the time building their own search engine, and they had similar problems that they were facing. And they had seen these papers from Google, and they said, well, this is interesting. We understand how it works. It's well described. Let's build our own implementation of this, because we will also need this. And this was only a couple of thousand lines of codes, and this became the Nudge distributed file system, because Nudge was the search engine that they were building at the time. Now, that search engine never went anywhere. What happened is that Cutting, they joined Yahoo, because Yahoo got interested in the stuff. Yahoo still existed or still had their own search engine at the time. And said, well, come work for us. The things that you have been building are interesting for us. Bring that here and start developing that further with us. So they continue to work on that and they rename it. So they renamed this Nudge distributed file system. They renamed their MapReduce implementation and they called it Hadoop. And Hadoop was the name of the toy elephant of Cutting's son. So that's where the name comes from. Now, Yahoo, before they went belly up, let's say, at least they made a couple of nice decisions for the community. So in 2008, they said, you know what, probably our search engine division, we will utilize Bing or whatever anyway. So we're just going to open source this stuff. And then everybody can utilize it. So they decided to open source Hadoop. So basically, Hadoop initially came from Yahoo, not from Google. Later on, the Hadoop project was taken over by the non-profit Apache Software Foundation, which is also the reason why with Hadoop, but also many other big data-related enterprise-like tools, you will see the name Apache being mentioned there. That's why it's Apache Hadoop, Apache Spark, Apache Storm, Apache Fluke, and so on, right? Because that's kind of the overarching foundation that manages all of these projects. And today, the hype around Hadoop has a little bit passed. I will see in a second why that is. If you look at raw Hadoop, if you don't install anything else, but you just set up Hadoop on your cluster of machines, then you have basically 4 components in there. One is a set of shared libraries that everything else uses, right? So Hadoop itself is written in Java, and a lot of Apache foundational projects and big data related projects are built on top of Java and the JVM technology, because that seemed like a good decision at the time, and it's kind of stuck around. The second part is the Hadoop distributed file system, which is basically a distributed C drive or a distributed hard drive, not on a single machine and a single hard drive, but over multiple computers. But it's basically a file system like any other. You can think of it as well, it provides directories and files that you can store and read, but underlyingly it's stored on multiple machines. Renamed from the Nudge distributed file system to the Hadoop distributed file system, so HDFS. MapReduce is then a programming framework that allows you to perform computations on data in a distributed setting. And then basically, if you have like a cluster of machines, and you have computations that you want to run on them, and you have data that you want to store of them, you also need a little bit of coordination. You also need a little bit of orchestration. You probably need something that can ask machines, well, I gave you a MapReduce task 5 minutes ago. Are you done with this task, yes or not? Or how busy are you? Are you ready to receive new tasks? Or are you still alive? Right? You might have crashed, and then I shouldn't send you anything else. So you need some central mechanism that can coordinate or manage your resources, resources being your computers that you have. And you also have several options, but for Hadoop, the basic kind of resource manager that does that is called Yorn, yet another resource negotiator. You have others as well, but that's the one that you get out of the box if you would install Hadoop. So okay, let's take a look at what this offers us, right? So HDFS, a distributed file systems to store data in your cluster of machines. Machines typically being commodity computers, so nothing special, just a bunch of laptops that you store in a rack if you want to, or a bunch of Raspberry Pis or whatever, connected over the network to this Yorn manager. To you, it appears as one seamless file system. So you don't even notice that there are multiple computers behind that file system. It would be as if you'd just be accessing your local file system on your own machine and storing your files there. You don't need to have this running. And even if you want to utilize MapReduce, you can think of other backends to store your files with. And today this is more common, obviously. Today you would preferably like go to Amazon and store your data in S3 buckets, or use some compatible thing on a VPS provider or on Google Cloud or on Azure. At the time, or for Google at least, they wanted to do that in-house, so they needed something to run in-house. It's one of the mechanisms that it utilizes for fault tolerance is that it will not just store every block of a file. So a file that you want to store is being cut up into pieces, into blocks. And obviously the idea is, well, if you think about it, if you have a file and it consists of 10 blocks, storing all of these 10 blocks on the same machine is probably not being a good idea, right? Because if that machine crashes, you lose all of those 10 blocks at once. Furthermore, even if it doesn't crash, but if you just want to read that data back out again, it basically needs to come from that single machine. Versus if you would have stored every block on a different machine, you can basically ask all of these machines simultaneously to start sending you the data and not overload them, right? So you can also get some benefits or parallelism there. Furthermore, it will not just store one copy, so it will try to distribute blocks evenly over the space that you have. Also not once, but it will replicate the data as well, meaning it will make copies of the data. And for every block, it will store 2 or 3 or more copies, again, not on the same machine. Again, for the reason of, well, if one of the machines crashes or one of the hard drives becomes faulty, no problem, we have copies, and basically the cluster itself can self-heal. It can detect that one of the machines has gone, and the cluster manager can say, well, we used to have 2 copies of this block, now it seems that one of the machines is gone, so I'm going to instruct that this machine to send a copy to another machine again, so that we can basically self-heal there. So the whole thing keeps itself intact in that way. So size of a typical block is 64 megabytes. Files can consist of more of blocks, and each block is being placed on separate data nodes. So there is like a name node that kind of, again, governs the organization, and then the clusters that basically store the data itself are then typically called the data nodes. To a user, if you're using Java, it comes with a built-in API where you can then access this file system, and it would be the packages that you use are a little bit different, but it's basically as if you would be reading out or writing files to your local machine. So it has directories, files in those directories. Basically, you can say, well, I want to read a file, and this is the location of the file on the cluster. This could be a 2 terabyte file, no problem. If you have space in your cluster, it will be split up into blocks and distributed. So it's basically like a massive distributed C drive running on a cluster. Does this solve your compute issue? Well, not really, because as the example here shows, and there are bindings to Python and C and so on as well, so the language itself doesn't really matter. But let's say, okay, you have found some Hadoop client or HDFS client for Python. You know that on the cluster there is like an 8 terabyte file of transactions that are being stored there. You want to perform some data science on that file. It's a tabular data file. So the first step would be, okay, I'm going to read in this file on my machine, open it up, pandas, data frame, and get started with this. Well, obviously this wouldn't work because yes, this file is being stored in a distributed fashion and it's large. Once you decide to read it back into your local machine and open it up in a pandas data frame, you are again using your local machine's resources, your local machine's memory, and it's going to say, well, I'm out of memory, right? So basically the compute aspect is not solved here. We have solved the storage aspect, but we're not really capable yet to compute in a distributed fashion yet. If it's smaller files, of course, you could read them in locally, but that's not really the idea of Hadoop as a whole. So like I said, other file systems continue to arrive as well, like 3FS from DeepSeek. And like I also mentioned, like a more common pattern today is to just use some sort of blob storage that handles all of this for you rather than you having to buy your machines yourself and basically use S3 or something which is compatible to that. So, okay, storage but no compute. So what solved the compute then? Well, that was MapReduce. And MapReduce is kind of, again, makes the promise of, okay, not only is now your data stored in a distributed fashion, but we'll also offer you a way that you can set up tasks, compute jobs on this data and have them run on your cluster of machines rather than you having to read in this file locally and then doing all of your data wrangling and processing stuff locally. MapReduce is a way to express programs, compute jobs, in such a way that they will be very easy to parallelize. And to also, in a way, parallelize them in a way that they're more or less fault tolerant, so that they can, if something goes wrong in the middle of a job, that you do not need to start from the very beginning again, but that you can kind of resume where things went wrong. So that's basically what this way of thinking in terms of how you express programs, so that's why it's called a programming paradigm, what it tries to offer. So it allows you to do something with your files in a distributed fashion. These terms are not new. Or Google by any means did not invent them. Mapping and reducing are terms that originally stem from the area of functional programming. Languages such as Haskell and basically a lot of languages offer map and reduce primitives. Even in Python, this is available as well. What map and reduce basically mean is, map means you have a list of elements and you define a function. So you also need to give me, so the input is both a list of elements and the input is also a function definition. And then using this function and mapping it to a list of elements then means that you apply this function on every item which is in that list. So in every element which is in that list. And so the result is a new list of values. So if this is my input list, 1, 2, 3, 4, 5, and I have a function definition that says, well, the result of x is x times x. If I map this function to this list of numbers, I obviously get this result. Reduce, as the name suggests, this performs a reduction. So it reduces a list down to a single value. So this also applies a given function, but now the result is not a new list of numbers. This is not applied element-wise, element by element, but it just takes the whole input list as a whole and reduces it to a single scalar. That's basically it. This is what Google took and said, well, these primitives are sufficient for us to come up with something. If we wrangle this a bit more, if we start from this, actually we can express a lot of programs in a way which is very nicely scalable and parallelizable. To do so, they made a couple of differences, and hence so did Hadoop, and they make some further assumptions, or they modify the system of mapping and reducing a little bit. And one of the assumptions that they make is that all of the elements that you have in your list of items, rather than it just being numbers, as on the example here, that they need to be of a specific format. And the format, every element is a pair of a key, which is unique. Could be anything basically, but some unique value, an identifier perhaps, or something like that, and a value. And for the value, they say, well, this can still be anything. It could be a number, it could be a piece of text, it could be itself a list, it could be an object structure or a data structure. That doesn't matter, but the keys are unique. We are also going to define a mapping function. So again, we will have to come up with a function definition. So that function definition will need to know that, okay, every element that I will be applied on will be a key value pair. And this function is free, rather than in the example that we saw here, where every input element maps to exactly one output element. A mapping function in Hadoop is free to output also either exactly one element for each input element that you apply it on, but can potentially output multiple elements for each input element that it receives, or can even decide to output no output elements. So it's more free form, let's say, could be 0, 1, or more output elements. And the output elements themselves are also key value pairs. So in the same form as what the input elements look like. Then, once all the mappers have finished, we will then apply a reduce function, and also a little bit modified, we will perform the reduction key-wise. So we will perform the reduction separately for each values that have the same shared key. So after the mappers have finished, it is possible that your keys are not unique anymore. It's even expected, and the reduction happens on a key-based level. Okay, we'll immediately see a couple of examples to show how that works. If you look for, okay, I want to become familiar with Hadoop and how does it work, and it promises so much and it's easy to scale, let me look for a tutorial or some examples to write some programs using this paradigm. In a lot of cases, what you will find is a word counting example. It's not the best example because you might think, well, I can write this myself in Python way easier, right? So this doesn't make my life much easier, but that's also not really what it's meant for. This is meant to deal with enormous volumes of data in a way which is easily scalable. That is the main purpose. It's also a bit strange that this is kind of the example that most sources come up with, and that they typically do not spend the effort to also illustrate some examples which are a little bit more intermediate, let's say. But okay, let's say we utilize this as a starting point. So I have a list of scraped websites, let's say. I've extracted the text, and so my input set of elements is, for a key, it's just some identifier, 1, 2, 3, 4, 5, and so on. Doesn't really matter. And the value is the text that I obtained from the web page. And now maybe I'm Google and I want to perform a calculation that tells me, well, how often does every word appear in this collection of websites that I have? And yeah, you can write a Python program to do this, but okay, maybe the collection of websites that I've scraped is not just 2 of them, but it might be billions of them, right? So again, how do I make this scale where I could say, okay, I can do this with a for loop in Python, and you read in every file sequentially one by one, and then you split the text up into words, and then you keep some dictionary of counts per word, but yeah, a little bit annoying because this runs on my machine, but how do I easily make this faster? Can I add a second machine and have it go twice as fast? That's already a little bit more cumbersome. And that's what this paradigm makes easy, or allows us to do in an easy way. So first I will have to define a mapping function. And for the mapping function, I will say, okay, what the mapper is going to do, it's going to take the incoming key value pair, so key 1, and the value is 2 plus 2 does not equal 3, for instance. And it's going to say, well, split up the value by just cutting up, by cutting on the spaces in the text, right? And then output pairs that have the form, the key is the word that you saw, and the value is just a number 1. That's what the mapper is doing. So it's just kind of splitting up the text in words like this. And then for the reduction, how you could express the reduction is basically saying, well, the reduction will take the list of values corresponding to each key. So for the key 2, there is 1 and 1, for instance, right? And maybe there's, like, we know that we have the number 2 in there and there as well, so dot, 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 right? We reduce on the level of 2. And the reduce is basically saying, well, you take in a key and a list of values that you have, and you're just going to take the sum and output the same key and with the sum. And then you have your final word count for each unique key. So the final output list has unique keys again. And the value corresponds with the word or the number of times that you have seen that word, so with the word count. Yeah, easy. The question is then, how can you leverage this into something that looks perhaps a little bit more to what you would done with or what you would have done with a simple SQL query, right? So can you perform data wrangling or easy data querying operations with this as well. And sure, you can, right? But this also immediately will reveal how MapReduce can be somewhat tricky. So let's say that now I start from a data set where I again have just a unique bunch of keys. These are object identifiers. And now my value is not a piece of text, but it's an object. It's a list of books. And for every book, I have the genre and I have the number of pages. And maybe I have a whole bunch of books, remember? So my issue is the more machines that I add, the more machines that I have in my cluster, I want this operation to scale virtually linearly. With every machine that I add, it should go n times as fast. So okay, I can define my mapper. My mapper function takes in a key and a value. And I'm going to say, well, how do you calculate an average? It's pretty easy. So you output the genre as the key and the number of pages as the value. So that's the mapping step that happens first. Nice thing here is that since every mapper works on a bunch of elements, or even on one element, it's easy to see how this scales. The more machines that you have, the more that you can distribute the work that's in the input list over these mapping operations that happen. If you have only one machine, well, then the single machine will apply the mapping of every input element to every output element in this case. If you have two machines, each of them can do half of the input elements. If you have three machines, you can split it up further and so on. So this very easily parallelizes and scales. So that's a benefit, that's nice. Once this mapping has been finished, we can define a reduce operation, so on a shared key and a bunch of values that we get in. And of course, the way how you calculate an average is you take the sum of the values that you received divided by the length of the values. And also this works pretty nicely in parallel, right? So because we reduce drama on one machine and another machine is busy with education, another machine is busy with thriller, another machine is busy with fantasy, they can do this in parallel to one another. If I have 4 machines, each of them can work on a single key. And indeed for drama, I saw 100 pages, 200 pages divided by 2 is 150. So nice, this seems to scale pretty easily depending on the number of machines that you have. What about memory consumption? Well, also pretty easy. If my machines are not very powerful, even if this input list is a list of 1 billion items, I can basically look at how much my mappers are capable to handle at once, right? At the limit, I can just have them go over element by element in the input, and then they can just yield their output element by element. So this is pretty contained. In the limit, I can split up the work in such a way that memory consumption here is being kept a lot under control. For the reducers, however, the story is a little bit different. Because here, for this drama guy, for instance, well, in this case, it's easy. It only needs to reduce 2 elements that it saw. But again, if this is still a list of 1 billion elements, probably it's not going to be a good idea that I tell this reducer machine that I have here, well, here I'm going to send you 1 billion elements and you need to perform some operation with it. Probably that billion elements is still not going to fit inside of its available memory. And so to do that, MapReduce applies yet another trick. And the trick that it applies is, well, the reduce operation should not have to wait until all the mappers have finished with their work. Also, the reduce operation is decomposable and should hence work on partial results. The reduce operation should be specified in such a way that it can first decide to reduce a subset of the total list of values and then perhaps reduce the resulting set of values that you still have for that key again, until you end up with a single value per unique key that you have in your output list. But that means that you need to write especially your reduce operation in a way where you expect or where you know that this can happen, right? So if you don't do this correctly, and our example that we just saw in that sense is not correct, because what can happen then? If we assume that we do not need to wait until all the mappers have finished, and if also we assume that the reduce operation is decomposable. Maybe there are 2 elements that arrive pretty early, drama 100 and drama 200. A reducer sees this and says, well, I can already get started, I'm free, so let me already reduce this partial result. So I apply our function, 100 plus 200 divided by 2 is 150. So I've reduced these 2 elements to that single element. And then later on, there is another machine which is perhaps a bit slower, which is still running mapping operations and says, well, I've now also produced an output element of a map step drama 300. Again, the reducers will pick up on this, and they will say, well, now I again have more than one element for the key drama. I have this one, drama 150, and now I have still this one, drama 300, so I have these two, so I need to reduce them again. So let me do that. 150 plus 300 divided by 2 is 225. But then you see the problem in the way how we specified this reduce operation is that now the final average that we end up with, the average of 100, 200, and 300 is not 225, right? The average is 200 instead. So we did not specify a reduction operation correctly here. So the correct way to specify it would then be that we have to rewrite our reduce operation, and where our values are not just the number of pages anymore, but they're like, okay, what is the running average that you have seen so far, plus the number of records that were used to construct it. And if you keep track of this as values, then you can also specify your reduction operation in a way where your complete result works correctly, because then you see 100, and this comes from a single element. So this is now what the mapper produces. The mapper just puts the number 1 in here. 200, and this comes from a single element. I reduce this, so 100 times 1 plus 200 times 1 divided by the length 2, and this is the sum of 1 plus 1. So you have 150 as your currently running average for drama, and I use 2 elements to do this. And then later, this element comes in again, so now we see these 2 elements, and the reduction now says, well, I need to do 150 times 2 plus 300 times 1 divided by 2 plus 1, and 3, which is a sum of 2 and 1. So now we have 200 as a result, and I use 3 elements to do this, right? My correct result is now in my value 200. This reveals that, okay, given that this is the paradigm that we work with, even specifying perhaps simple querying operations, like something like an average, we do need to be a little bit careful in the way how we write those out. If you're now going, whoa, this seems like a completely cumbersome way on how to specify programs, yeah, sure, right? You would be right. In a way which, yeah, is very easily parallelizable, so that's a benefit, that's nice. But if I would then ask you, okay, now go ahead and implement a random forest or a decision tree on top of this, might not be so easy, right? So we're still quite off from there. You will be given access to a piece of Python code without you having to install Hadoop yourself. We don't do that anymore, but where you can try out some of these examples about averaging and so on, using kind of a simulation on how MapReduce works, just with a single machine, if you want to experiment a bit further with this. Furthermore, what is maybe also not very appealing is that in base Hadoop, yeah, how do we write these programs? Well, again, we use Java for that. So we express our map operation and our reduce operation as Java programs. There exist bindings to other languages as well, but Java is kind of seen as the native language there. And then the idea is that you package your reduce and mapper functions up in a package, in a zip file basically, a Java archive file, a jar file, and you send it off to the cluster, and then you just wait for the results to appear. And typically you will write these programs in such a way that where does the data come from? Yeah, here we just had a list of data, right? But typically you will write them in such a way that your data is extracted from HDFS, and also the intermediate results of operations are also written out to HDFS. And the reason why this happens is, well, obviously if the resource coordinator sees that there is like a slower mapper still busy working on something, and in the middle it crashes, so it never produces its output, well, okay, fine, we don't need to redo this part again and this part again, we can just ask another machine to work on this input element and resume from there. So also kind of resuming operations, even if a mapper goes down in the middle of its work, or reducer goes down in the middle of its work, the intermediate results are always stored on HDFS, so we can always continue from there with machines that are still healthy and are still alive. So it has a lot of nice benefits with that regard as well. It's only a little bit cumbersome to use. And so if you look at the code that you would have to write, I mean, it's pretty verbose. It's not the most fun code to write to do data wrangling with, but certainly possible. So this is then an example how you would send it to the cluster, and you can keep track. Basically, Jorn tells you like how things are going. I'm 0% done with the map operations and 0% done with the reduce operations, and over time your job is complete and your data is stored on HDFS. So I can take a look at, okay, what did you output? Ah, yeah, indeed, there is my list of words, my final list of words that you put on the HDFS cluster. So that's basically how that thing works. The mapper and reducer components in how you specify a job are the most important ones. The full framework also comes with a couple of other steps, mainly like partitioning, maybe you have like your machines geographically distributed and you're a bit opinionated in which mapper should do which part of the input or which reducer should do which part of the intermediate output that the mappers have generated, or how should that intermediate output be distributed over the reducers, or how should it be shuffled. You can basically tune that a bit, but the main compute, the main what does the program do, is expressed by these mapper and reducer functions that you write. The rest is basically kind of tweaking and managing it a bit. So it requires a certain, well, let's say skill set if you then want to write programs thinking in this MapReduce framework, right? And it promised a lot, but a lot of kind of early adopters of Hadoop got kind of confronted by the message, well, damn, this is not so easy as we thought this would be, right? We come from something that's running on a relational database that was actually doing pretty well. We had SQL to do all sorts of data wrangling, and it was also going rapidly fast because our database administrators have spent years on constructing indices. And now we have this kind of new way of working where we start from something that's basically unstructured or maybe in some object structure, and we need to express all our queries that we want to do in these nasty MapReduce programs. So what did we actually gain? Well, what you gained is a way, an offering where you could say, well, contrary to a traditional database that also has these kind of transactional properties of atomicity and so on, which typically do not scale well horizontally, now you have like a compute framework where you can easily say, well, let's buy 100 computers extra and the work can go 100 times as fast because we write our programs in a way that they're very easily distributable and resumable. But for most companies, they were not running Hadoop on 100 machines or 1,000 machines. They were running it on 3 machines. And so they never really experienced the benefits and the typical compute tasks that companies have when you deal with tabular data, for instance, are also not of the sort that you would have them run on 100 machines, and where they're more preferably or easier suited to run on maybe a couple of machines, which are then have higher memory internals. So not everybody is Google, and not everybody does the same sort of compute as a search engine does, obviously. So being able or being capable to handle big data workloads in a way which is fault tolerant does not mean that these workloads become automatically way faster, right? And this was kind of the first oops moments of Hadoop adoption, where the realization was, yeah, being able to handle large data sets does not mean that you can handle them faster as well. So, okay. I already mentioned Jorn a bit, which is the resource coordinator. A bit of background: in Hadoop 1, version 1, this resource management was still set up in a way that it was like a little bit fragile and with larger workloads could crash. So that is why in Hadoop 2, it was split off into 2 components, and why they decided to split up the resource management capabilities in its own thing, Jorn. In Hadoop 3, this is mostly the same. It's a bit of detail. But remember, kind of resource coordination then basically means, well, what keeps track of what machines are doing, who should receive which subtask, who should start mapping, who should start reducing, basically the coordination of this all. So standard Hadoop, basically it's not a turnkey solution for most environments. It's a big hard drive, let's say, and a way to write MapReduce programs in a way which is not fun to program at all. So that is why companies and integrators and other open source projects as well, they started building a lot of components on top of this base framework, on top of this base storage framework, and on top of this base compute framework that you have. And you see a whole list of them listed here. There are many more. And basically now you kind of understand, okay, there is a reason for this, because with just raw Hadoop, you don't get that much out of the box. This ecosystem has become so broad and at some point was so large that you even had to run specific kind of projects that could monitor your whole cluster and all of these sub-projects and see how they were doing. So at some point in time, this is what companies were trying to set up and get started with. And companies like Dell and Oracle and HP and IBM and Cloudera and Hortonworks, they all had their versions where they took these open source packages and they basically combined them. They added some support on top of this. They put their logo on the website, and they basically sold this as kind of a big data platform, basically. That is what a big data platform meant at that time. The first kind of letdown then that came out of this is, okay, fine, we have all of this running now, or we have MapReduce, a way to store data in a distributed format. But again, most companies came from the world of relational databases. So how do we query this thing, right? Every time you have a new sort of data store that becomes popular, at some point you will get a question, yeah, but how do I run SQL on top of this? Because this is what my BI tools are using, and they want to integrate or connect to this. This is what Power BI uses or Tableau uses, so we need a way to run SQL on top of this thing. It's a file system, okay, good, it's distributed, good, MapReduce, nice, but okay, we need SQL to query this thing. And this was a problem, that this was not possible. And so in 2008, this problem got solved to some extent by, again, an add-on project, which was called Apache Hive. And this came from mainly Facebook at the time, who were using this and said, well, okay, we also face this problem. We do want to be able to query data that we have stored on HDFS. And we don't want to do it by writing like nasty MapReduce programs to run like averages and stuff like that. We would like to express our queries using SQL because that's what everybody uses and all the programs use anyway already. So the release of Apache Hive. Okay, the way that it took to do this is, first of all, you need to store the data table somewhere. Okay, let's dump them in some specific format on HDFS. HDFS is agnostic in terms of what the files are that you store on there. So we come up with some sort of columnar-oriented or row-oriented binary representation format for tables, probably split row-wise so that we can easily distribute them on these different machines that we have in our HDFS cluster. Fine. And then we need something to perform SQL operations over these files. Okay, if you only have raw Hadoop, what's the easiest way to do that is we're going to write a parser that's going to take your SQL query, like something simple such as select this and this and this from the books table, and I want to group by genre, and I want to order it by genre. Well, let's just write a program that can convert this SQL query and automatically converts this into a single, preferably, or in the worst case, maybe multiple MapReduce jobs to produce the final output result table. So basically, it takes over the work of you having to write MapReduce programs yourself to do this, and it basically automates that for you. So that is the approach that Hive took. Basically, a SQL parser with a conversion step to MapReduce jobs. And there were other ideas as well, similar in this vein. Something like HBase, which also wanted to provide kind of a database on top of HDFS and MapReduce, but which did not bother to implement SQL, which was key value oriented, no expensive or no complicated queries, basically very simple key-wise get and put operations that you could do. And the answer of HBase at the time was, from the moment you would like to run a more complicated query, we are not going to bother. You have MapReduce, write it yourself using MapReduce. But again, this is exactly what people didn't want to do, hence why Facebook came up with Hive. Before that, there was also Pig, and again, trying to offer a similar answer, saying, okay, we get it that writing these MapReduce programs there, that's maybe not so easy, so we're going to come up with a different programming language that also automatically converts itself into a bunch of MapReduce jobs. Similar in nature, but now not doing the conversion from SQL, but doing the conversion from, let's be honest, a programming language that looks a lot like SQL mixed with Fortran from the 70s and COBOL, right? So also not something that people really wanted to utilize. It looks very archaic, very cumbersome to utilize. People still wanted to use SQL. That's what we know, and that's also what these business intelligence tools know. So Hive was definitely a saving grace for Hadoop at the time. Finally, we had something that we could store tables and run SQL queries on top of this. But it was definitely not perfect. First of all, it did not implement the full SQL standards. It did not implement the full SQL language. So if you wanted to perform complicated joins that you could easily do, again, with your relational database, was not supported. To some extent, not so bad, because it does support like a large subset of the SQL language, so okay, still fine. But the main problem is that underlyingly, your SQL query still gets converted to a MapReduce job or jobs. And I just said, well, that MapReduce does a lot of intermediate saving and loading of what all these mappers and reducers are doing, because it wants to be able to be resumable at any point if a machine would go down. And there is still like the underlying assumption that, but probably you're going to run this on a cluster of 1,000 machines, right? So then it's very scalable and things like these can happen, but this is not how companies are using it. Companies are running it on just a couple of machines. And so again, you have swapped out your relational database for something that looks very much alike, but has suddenly become way slower, right? And I myself remember from the time having experience with like initial pilot experiments at companies working there as a contract researcher, where the switch was made from like DB2, running a relational database by IBM, loading all the data into Hive, performing queries there. You could go for a coffee break and perhaps also lunch before your query was done running, right? So again, you can handle very large workloads, but If the data comes from something that's in a relational database already and worked there, you probably do not have those large workloads to begin with. So again, big does not mean fast. So a little bit of disillusionment. Yeah, companies like Hortonworks, they were trying to come up with their own alternatives, like Apache Test, where they tried to step away from MapReduce especially, because the notion was becoming clear that, okay, for most analytical and data wrangling workloads, this kind of MapReduce way of thinking is perhaps not the right way to think about things. We are not a search engine. So they were trying to come up with alternatives, alternative computational frameworks to handle it instead. And Cloudera and Hortonworks, they had like their own ideas, Apache Test, Impala, where they started to move away from the MapReduce paradigm and offer this as some sort of intermediate solutions, some better than others, a little bit of a Wild West in terms of, okay, how can we make this thing faster now and better oriented to what organizations actually want to do with their data. This was a whole big mess, and hype was starting to meet reality. So around this big data was reaching kind of a fever pitch up until 2014, and by then people were kind of moving away, and we saw that what happened afterwards is that people were becoming more interested in artificial intelligence again. Deep learning was entering the stage. This kind of Hadoop situation with Hive or Tez or Impala was kind of failing to fulfill its promises. And if you look back today, if you do have like large tabular data sets and you want to have a mechanism where you don't need to manage your database yourself, but you want something which is automatically scalable and which is also fast, today you would probably look at a provider such as a Snowflake, for instance, a very large company nowadays, or something like a ClickHouse or a Dremio or something like Redshift, which have basically offered cloud-oriented solutions and which have mostly gone back to things that relational databases were already doing and just becoming way more aggressive in the way how they construct their indices under the hood. So a return to maybe the older approaches, let's say, but put in the cloud and put with automated indexing mechanisms and automated scaling mechanisms. Still, even today, if you hear or if you have discussions with architects and they draw their pyramids with their raw data and prepared data and their pipelines, this is the thing that they are mainly concerned about. Like, how do we store data? Where do we store it? How do we manage it? And so on. We have SQL now more or less available to us. We haven't yet touched the question of, okay, but then how do I utilize this data, like to train models from the analytical side? That is still unanswered. So most have realized that today you will not hear a lot of companies getting started with Hadoop anymore because for your data, they're not the right fit. So you will probably use a more cloud-based database. Now, even then, even if we utilize something like a Snowflake, in essence, we're back to the BI days of doing analytics. Yes, our data lives in the cloud and it's nicely indexed, and Power BI can connect to it, or Tableau, so we can do reporting, we can make dashboards, we can make metrics. But if you think about machine learning or predictive analytics, we are not that much further yet. Things have become more scalable and more outsourced and more software as a service-like, but except that we have perhaps a more annoying data storage layer. So how can we utilize these technologies, Hadoop and friends, let's say, probably not Hadoop, but something similar to it, to answer the distributed analytics question? Like, where is my distributed data frame and where is my distributed training of my random forest, let's say? So again, also for this, just as it was for SQL, also MapReduce here is definitely not the right answer to perform this sort of use cases with or jobs with. Why? Well, think about it. Implementing a decision tree or random forest or something like a gradient boosting machine as a bunch of mapping and reduce functions is probably not going to be very easy, right? It will also be slow because of this in and out swapping of data from and to HDFS. At some point, there was a project that tried to do this called Apache Mahout, which never got very far. They tried to do this, but they also found that it was very slow. Now, luckily, we had like one follow-up project in 2015, the arrival of Apache Spark, which did make a lot of changes and did offer some ways out of this mess, both for the querying side of things, but also for the analytics side of things. 10 to 100 times faster than Hadoop. Okay, so it was time for a Spark. Now, if you read these Apache project kind of one-liners, they all say more or less the same thing. We'll see some more examples or modern examples as well. They all want to do real-time and processing and SQL and wrangling and analytics. So it's a bit hard to make sense of it all, but certainly Spark is one that was, and still is today, that's why we also take a look at it, still heavily adopted by organizations. Not all that they're doing like very complicated tasks with the Spark compute platform, but simply because it offers appealing ways how you can handle both large sets of data, streaming sets of data, building machine learning models on top of a nicely distributed setting. So what did Spark decide to throw out? Do we throw out a resource manager? Well, not really, because we're still running in a distributed setup. We will still have to perform some sort of resource coordination. So we can keep Yorn. Now, Spark also comes with its own alternative called Mesos, which is an alternative resource manager. It also comes with a built-in resource manager, so you don't need to use Yorn. Any resource manager basically can work. What about HDFS? Well, now you don't need to throw that out. If you have HDFS running and your data is there, fine. We can use it as a data source. Why not? But we can also utilize lots of other data sources as well. I mean, compute does not really care about where the data comes from. Maybe you have it in Amazon S3, or you have it in Google Cloud, or you have some data in Hive tables already, or in HBase, or you just have a file on your, or a file system somewhere on your network where you have a bunch of JSON files or Parquet files or CSV files. That should also be able or act as a data source that we can utilize, right? So we don't really care where your data comes from. If you don't want to use HDFS anymore, you don't have to, right? You just connect the cluster to some set of data sources, and that's fine. Our main concern is to perform compute on that data, and also at the end to do some machine learning on that data as well. So also this we do not necessarily need to throw out or need to keep. What we do throw out from Hadoop definitely is this MapReduce paradigm. So that's not something that we're going to do anymore. So Spark moves completely away from MapReduce, and it replaces it by an alternative way to set up jobs. And the alternative way is to offer compute primitives, which will allow you to construct a directed acyclic graph of steps of operations. Quite similar in how modern deep learning libraries, such as TensorFlow and PyTorch, also construct an underlying compute graph over tensors as well. This thing does something similar, but the compute graph is constructed not over tensors as an input element, but on top of another input element that we'll see in a second. It's then going to take a look at this graph of steps that we need to perform. And acyclic means that there are no cycles in your graph. Otherwise, you would run into a non-ending loop, right? So there need to be like a set of inputs and a final set of outputs that you can do step by step. And then you can take a look at this graph of steps, and then you can kind of analyze it and say, okay, if I have 3 machines, how do I cut up the steps in this graph in such a way that I can utilize the availability or the CPU power that I have by these 3 machines in a way which is as efficient as possible. So that stays. Also what stays, or not what stays, but what we're going to differ now is we're not going to assume, because we're not running with mappers and reducers anymore, so we're not going to assume that now we have a cluster with 1,000 machines and they can all do little map operations and little reduce operations and they swap back and forth to HDFS. We only have 3 machines, let's say, and we're going to assume that these are relatively beefy machines, right? So we're not going to be swapping in and out all the time. If we cut up our graph or construction of steps that we need to perform, and there are like 5 steps after each other, right, where we start with some list of data elements and we first do step 1 on it, and then step 2 on it, and then step 3 on it, and step 4 and step 5, it's a good idea to keep this bunch of 5 linear steps in the same machine. Right? And to not do back and forth swapping all the time, and to just say, well, the best way, the most efficient way to do this is to keep that with that single machine, and preferably then also a machine that has sufficient memory to do that. Right? So maybe making the cluster a little bit smaller and not swapping and distributing steps to such an extreme extent anymore. So in a way, a little bit of a step backwards to this massive parallelizable way of thinking, but maybe a little bit of let's say a mixed approach. So that's offered by the Spark core engine. And then they said, well, on top of this, we're going to implement the SQL engine. And thanks to this SQL engine, once you have SQL running in a way which is fast, not like we did with Hive anymore, but now in a way which is more native, This will offer us a way to express data frames, because if you have SQL, you basically have a data frame. Everything you do in Pandas, you can do with SQL as well. So if you would write it as in Python, like .filter or .select, you can basically convert that to SQL. And if your SQL is fast, you can do that, right? You're just working with tabular data. Once you have tabular data running in a way which is efficient and that you can do your querying and data wrangling and your pre-processing in a way which is fast, then you can start thinking about adding machine learning on top of that. And you can also start thinking about adding streaming data on top of that. You can start thinking about working specifically with graph-based constructs, but Spark never became like a champion in this area, right? Some graph databases did a bit better there, but there are companies also in Belgium utilizing Spark for graph computations, in which they call GraphX. Or on Spark, Spark runs on Python as well. It has bindings to Python, it has bindings to Java and Scala as well. But R came a bit later, which is why it gets its separate block on this slide. And then they also at some point experimented with like approximate SQL, probabilistic SQL, which they call Blink, but which also never became that popular. So key components are Spark SQL, Spark Streaming, and MLlib. Now, what is the primary or the prime abstraction that these operations that we're going to express in our directed acyclic graph that we perform on data elements, what do these data elements then look like? Remember, with MapReduce, we made the assumption that every element in my list of inputs had to be a key value pair. Spark also starts from a basic representation of what data is, but it looks a little bit differently, and at the start, it's actually very abstract because it makes very little assumptions. Yeah? Yeah. In the case with the deep learning example does not utilize mapping and reducers. The similarity is that just as what Spark will do in like a series of steps that look like a graph, also in deep learning, if you write like Keras code and you define your model, underlyingly it's also a graph that gets constructed there. The prime goal there not being to then cut it up and distribute it over multiple machines necessarily, but the prime goal being how to work out the backwards computation, to have the gradients flow backwards, basically. That is there what that graph construct offers you. But the similarity in how you express like the forward operation as a series of steps and that gets converted into a graph, that is quite similar in both approaches. Yeah. Very often, if you talk about compute and you express things as a series of steps that you want to do on data, very often the underlying data structure there will be a directed acyclic graph. So that is the case for deep learning, is also the case here. Not. So with MapReduce, you can't. And MapReduce tasks are also not expressible as a graph easily. Well, if you would express them as a graph, it would basically be first you do all the mapping and then you do all the reductions, right? So that is a separate construct, which is also why it's less suitable for these sorts of workloads. Yeah. So again, having or expressing some sort of deep learning algorithm with MapReduce, I wouldn't know where to begin, to be honest. So, so hence why this is also not a good paradigm for these sorts of workloads. Yeah. So here Spark says, well, your data that we will express or steps on or operations on, we will call this a resilient distributed data set. And a resilient distributed data set is, again, just a list of things. And what these things are, we don't care yet. It could be pieces of text, it could be images, it could be numbers, it could be whatever. So the Spark core does not really care about this. The only thing that it cares about is, okay, you have a long list of elements, and we're going to distribute them. So we're going to, it should be able, or we should be capable to split up this list of elements and distribute them over the different machines that we have. And then you're going to tell me what you would like to do in terms of operations with this list of elements, the steps that you want to perform. And either these are transformations which convert one RDD to another RDD through some compute step that you need to express, you need to tell me about. Maybe you want to add 1 to every number that you have in this list, and so you know that we are working with a list of numbers, I don't know, but you tell me that you want to add 1. So I can take that step and then I can figure out, okay, this is something that I can easily do in parallel. If I have 10 machines each 10 of them can work with 1/10 of the original list that you started from, right? So that's hence the underlying graph idea that appears. And then you also have actions that maybe you want to count the number of elements in this RDD. Then you're not changing the elements themselves, but you're like summarizing again the list of RDDs. And again, it's done in such a way that this is to some extent fault tolerant, that this is resumable and so on. So these underlying concepts do stay. So a collection of elements partitioned across the nodes of the cluster that can be operated on in parallel, and transformations and actions will then do things with this RDD. Now, that means, okay, you can start with an RDD1 that you define in your favorite programming language, maybe a bunch of lines of text. So every element in this list of elements, every element is perhaps a piece of text, or is perhaps a row of a vector of numbers, for instance. And then you can express steps such as I want to join this to another RDD, and I want to do group by, and I want to do a filter. So ultimately, we would like to express our operation as something like this. This then gets converted to a compute graph, a directed acyclic graph, as you see here. And then basically the thing figures out, well, these two steps, they can run in parallel because they're independent on one another. And then there is another machine that needs to get working on these three steps. And then there is a final operation that consists of these three things to produce the final output list. The benefit here, and this is the key difference with MapReduce, is that here you can see, well, it doesn't make sense that we give this step and this step to two separate machines and that they need to store their intermediate results that then gets loaded in by a third machine. These two steps can easily be handled by the same machine. And these three steps, these can also be easily handled by the same machine. So do not try to decompose completely into very granular, like MapReduce did, map and reduce steps, but try to keep things to some extent together to avoid like data swapping in and out. And hence why this is more performant than what the MapReduce paradigm could offer us. Also, and I already mentioned this, also Spark is written on top of the JVM. So yes, you can express your operations through a Java program. Scala is also quite popular. If you go work at Twitter, for instance, or X, they are running lots of querying and analytical operations on their user base using Spark and operations or programs written in Scala. Most companies here, if they work with Spark, or most companies overall, if they work with Spark, they mainly do so using Python. So Spark exposes these operations that you can do with these RDDs in multiple programming languages. Important to note is that whatever language that you utilize, here it just becomes a language that you utilize to express the operations that you want the cluster to run on an RDD that will be loaded in from some sort of data source, right? If you press enter, even if you use like PySpark in Jupyter Notebook locally, this does not get ran on your own machine. These are then commands that are being sent to the cluster, and the cluster runs those commands, right? The idea is that we have the cluster do the work. We just use the programming language here to express the operations. For assignment 3, you have the cluster, or you have the single Spark node also running on your own machine, so you're not really sending it to a different machine, but ultimately in like an operational setting, that is what you would do, right? You would open a PySpark, but underlyingly what this thing actually does is it connects through the cluster through this Spark context object that you have. And basically every method that you call on this SC object will be sent to the cluster to be executed there in an interactive setting which Python provides. If you'd be using Java or Scala, then you're not really working in an interactive setting, then you just write your program first, you package it up, you send it to the cluster, and you have it do its thing, right? Or you schedule it to be run every so often, for instance. So it's not running on your local machine. Now the programming language just acts as some sort of glue language. So PySpark isn't only just the driver program. That's the program that does run on your own machine, and that is the program that will set up or will provide you with this Spark context object, which typically is then just called SC, but this is then that object that lives locally on your machine. Every method that you call on that object, such as, well, I would like to read in a text file, right? This is performed by the cluster. This handle that you get here in this variable text file, this text file is not being read in and being sent to your machine completely. It's just a handle that you have over the network to the cluster that you can continue to use to then ask, well, okay, now return me the count of elements that you have in there. It's the cluster that will perform this operation. Give me the first element that you have in there. Of course, if this text file would be 2 terabytes large, and you would ask your cluster to say, okay, now give me back all the contents and load it in as a local pandas data frame, yes, then you might still crash your local machine, right? So important to think about this. These are commands that are being given to the cluster and everything lives there versus, okay, now I'm deliberately asking it to give me back all the data in my local environment, and then, yeah, it might be that you still run out of memory, right? So then you're back to working locally, obviously. So the way how you write your programs is, of course, by interacting with that cluster for as long as possible. So also these tutorials that try to make it easy and say, well, just load in the data using Spark and load it in the pandas data frame. You're not really using Spark anymore at that point. You're just back to working with pandas, right? And you didn't need Spark to begin with. So also like this filter operation, again, Spark doesn't care like what is in this RDD. With text file, it basically will put every line in the text file as one element in the underlying RDD. That's what text file does. But then you can say, okay, I want to filter, and I know that every element is a line of text, and I only want to keep the elements that have the word Spark in there, right? And again, this is an operation where Spark can decide what's the most efficient way that I can do this. So I have already split up the RDD, where the file was 2 terabytes large. I can see that I only have three machines, and they have 4 gigs of memory each. Well, then probably I'm going to have all 3 of them read through the file, read the lines there, but I'm going to organize this in a way where I do as little data swapping as necessary and in a way which is as efficient as possible. So that's the Spark context. You have been also working with this already. So no data is loaded in the client unless you perform a 2 pandas. Then, of course, you load everything in your local machine. Alternative to the interactive mode is you can also still package up even Python programs, and you can use another binary, Spark submit, and say, well, I have a little Python program here. I'm not running in Jupyter Notebook. I don't want to run in an interactive session. I just want to take this Python program and send it to the cluster and have it perform its work for me and let me know, or I will see when it's done, because some new object will appear on S3, on HDFS, or whatever output sync that you plan to utilize. So that's also still possible. The basic RDD API, the operations, so the transformations and the actions that it provides you with, the set is quite limited. It's filter and also our old friends, map and reduce. So you might think, oh, okay, you just said that it doesn't use map reduce anymore, so why does it say map and reduce here? We can use join with another RDD, where I will probably also need to express how the join needs to happen, because again, RDDs can be elements of anything. How do you join 2 RDDs if the elements are lines of text? I will have to tell you how to join them, right? Same for taking an intersection. We can sample from it. We can count. I can ask for the first element. I can do a reduction. I can take a sample. I can save it as a text file. I can do a for each operation where I also need to express my own function in terms of what needs to happen for every element in this RDD. So not a lot, but sufficient. You might also think, okay, map and reduce, but you just said that we step away from that. It's not because you step away from MapReduce as a framework in terms of how you're going to organize your computational steps in a way which is parallelizable, that the functional concepts of mappers and reducers could not be utilized anymore. So the concept is still, I want to map a function to an RDD, a list of elements. I want to reduce a list of elements. But now it does not get converted into an execution scheme where I have 1,000 machines and they all start mapping a bit and reducing a bit. Still a directed acyclic graph gets constructed from that. And if you only have 3 machines, I'm not going to have these mappings happen one by one and having intermediate results saved to HDFS and then loaded back in by the reducers. Here the underlying graph system will be smart enough to say, okay, but actually we can have the same machine do these 1,000 mappings. We don't need to save data back out and in again. That's just a single machine that can keep busy for a while for a longer amount of time. Right? So the expressions or the operations can be similar, but the way how you execute them is different. You have Spark running yourself, but if you want to play around with a couple of other kind of examples to get to know this RDD system a little bit better, there will also be like some examples posted in the background information where we use dummy RDD, and that's again a simulated kind of class that runs locally that expresses the same list of operations but does not bother to have them execute on a real cluster. It just runs them locally, but it shows you kind of the operations that you can perform. So we can say, okay, I want to make an RDD out of a Python list. We can do that using Parallelize, and normally then this list would go live on the cluster somewhere, and then I can say, okay, give me the count or map something to that and collect the results and send them back to my local machine again. So some other examples where we read in a text file and so on, where we filter, etc. Okay, that's all nice and dandy. We now have a distributed list of elements and they can be whatever. And yes, it's more efficient. It's still fault tolerant. We have not all this intermediate swapping of data, so we're not as slow as MapReduce was. We can, instead of buying 1,000 cheap machines, we can buy 3 to 5 beefy machines, which is probably a nicer kind of proposal for most organizations. So that's all nice. But if we look at these operations like map, reduce, reduce by key, remember, now the execution is different. It's based on the directed cyclic graph, not on massive disk swapping anymore. But from our perspective, as a user, it's still low level, right? Okay, fine, I can do things like reading in a text file and then filtering by words or making a word count like we did before, or I can maybe divide numbers in a list by 3 and so on. But still, where I would like to end up at is, can I now have something where it really feels like I would be working like I would be in Pandas, where I have a data frame available and a data frame that's distributed now, and where also the compute operations on that data frame are distributed. In other words, I do not want to work with low-level methods such as filter and flat map and group by key. I want to have .select, .filter, .group, all the things that I had in Pandas, basically. But on top of this, it turns out that Spark will offer something that will make this very easy for us to get there. And this is, of course, then the main benefit of Spark. It's not really this low-level RDD thing that no one wants to utilize. It comes through the mechanism of Spark SQL that also offers us a data frame concept. We'll take a look at this in a second, but first let us go for a 10-minute break. So low-level RDDs, very flexible, but in most of our use cases, we can be a bit more specific. And if you think about what a data frame, if you would have to express it as a distributed set of elements, then what is a data frame? Well, every element is a row, basically is an instance. And what does every row look like? Well, a row is a bunch of values where every value is associated most likely to some particular column name, right? And so it's relatively structured. So we could still express it as an RDD, and that is exactly what Spark will do, is saying, okay, now on top of this, if we impose some sort of schema, a schema which will tell us what the names are of the columns that you have in a data frame and what the values are for each column, well, then every element of that RDD becomes a single row, a single instance in that data frame. And then we probably are also on the way to expressing more higher level operations that we can execute on such a data frame, very similar to what Pandas would give us. Now, as an intermediate step, what we can also do is we can also think working on a query engine, again, a parser for SQL, a SQL engine implementation, which Spark calls Catalyst. And there they say, okay, given that you have an RDD where every element in your RDD represents a row, again, in a table, then we will write something, or we will offer something that allows you to write SQL statements to perform queries on that RDD, on that bunch of rows that you have then in what is a table, which again will underlyingly be expressed as operations that will happen on this RDD, that is still the underlying core abstraction, but in a way which will then again run way faster as what we could do with Hive, for instance, because Hive converted the SQL expression to a MapReduce bunch of jobs, versus here we still can run on top of this directed acyclic graph execution framework. So if we now implement a SQL parser, again called Catalyst, and with some query optimization there as well, like a typical relational database also does, we have probably something, a mechanism that allows you to query your data, your structured data, in a way which is way more efficient. And then you're well on the way to also exposing data frame primitives or data frame methods on top of that as well. And then finally, you have something where you can tell Spark, I want you to read in a JSON file, and if you then show it, it has immediately converted this into a data frame object. And now finally we come to the point where you can say, okay, tell me about the columns in there, what are these, and select me a column in there, and I want to maybe add something to a column, I want to do some pre-processing, filtering, grouping bys, and so on, or even just writing plain old SQL, because also all of these operations like select and filter and group by, they look as how you would write stuff in Pandas. Contrary to Pandas, however, here everything first gets translated to a SQL operation, which then runs on top of this Catalyst engine. if you execute operations in Pandas, they run directly on the internal data structures, which are now represented as arrow data structures. If you would be using DuckDB, it does something very similar. If you would write Python code, it also executes it as SQL statements. Again, this data frame now is itself still an RDD. It's just an RDD that is a little bit more structured. It's just an RDD where we know that every element in that RDD is now a row of a tabular data set. It's a row in this data frame, right? So underlyingly, there is still this core abstraction of this RDD. So also this data frame can be 2 terabytes large. It still lives on the cluster. It's still distributed. Not every row needs to be present at the same machine there. So that is still the case. We have just made the elements of our RDD a little bit more structured, and by doing that, now we can think of them, or we can work with them as we would with normal data frames if we would be working locally as well. So finally, we have a concept of a distributed data set. So a data frame is a distributed collection of data elements. So it extends the free form elements that you normally have in an RDD by imposing that every element is organized as a set of values into named columns. So it imposes additional structure on top of RDDs. And hence, this also allows you to provide a higher level abstraction towards working with these data frames. And as a data scientist, typically, you would be working with this level of abstraction rather than working with the lower level RDD set of abstractions. Because most of the things that we do is with tabular data anyway. So these are the, so you find that in the PySpark.SQL packages. Data frame, row, column, and so on. Window operations is in there. So all the mechanisms that you would have with a local data frame library, but now living again on your Spark cluster. What can you do with that? Well, read the documentation basically, right? But again, it's things that look quite similar to what Pandas offers you. Drop missing values, drop duplicate rows, filling in missing values, cross-tabulation, a join, a sample covariance matrix calculation, and so on. So all these low-level primitives that you would expect a data frame to be able to do are in there as well, right? An aggregation expression, a select, a group by, an intersection, a join ordering, a random split, replacing, union, and still this to Pandas, but remember, then you load in the full underlying distributed data frame on your local machine. So then you might run into trouble. Applying a function again on every row in your data frame, which basically offers you anything that you want to do with it, and this will also be distributed over the cluster. So nice that we finally have a mechanism of a distributed data frame. It took a while to get there, but at least we are there now. Can be loaded in from any sort of file that you have. Again, that doesn't change. Any sort of file that can store some sort of tabular structure, from a CSV file to a JSON file to a Parquet file, can be loaded in by Spark as a distributed data frame. And if you want to, you can convert it back to a standard RDD and then use your low-level RDDs as well, and vice versa. You can start from a normal RDD, but then you would need to tell Spark, okay, but how do you convert this RDD of elements? What are the columns in there, right? And for the text mining exercise, if you do not use Spark structured streaming, but you just use Spark streaming, that thing represents all of the elements that it collects every 10 seconds or whatever as a list of, or as an RDD. Every RDD might be containing, for each of its elements, a piece of text, maybe perhaps formatted as a JSON structure, like is the case with the assignment number 3. Well, if you want to then use the data frame API, you first need to tell it, I want you to convert this RDD into a data frame. And by the way, there is JSON in there, so you will have to parse that and get the columns out of there to construct a data frame out of that. So then you do need to tell it what the schema is. Spark R, not much to say about this. Like I said, this came a bit later, so this is why this has gotten its own name. This is basically the implementation of the Spark data frame API, but for R. So you can utilize normal R data frames together with packages such as dplyr, for instance, but where this data frame, again, now is not something that is stored locally, but represents actually a distributed data frame that's living on your cluster, right? So likewise, you can write normal-looking R code, but now the thing is running on your Spark cluster. So there is no low-level RDD representation for R. You don't get access to that lower-level stuff. You work directly on the data frame level. Spark also makes a difference between what it calls data frames and data sets. For us, the difference is not so important, but it is important if you would be working with a language that is compiled or that is strongly typed. So for Python and R users, you will stick with the untyped API, which is basically the data frame API. And the data frame API says, well, a data frame is basically a data set where every element is a very abstract row kind of thing. And a row has a bunch of columns, and every column has its own name. And if you then want to get the value for a certain row given a column name, you will get the value of that attribute back. The difference being that at compile time, the compiler cannot check here whether the things that you're fetching out of this row, that you're using the right names of the columns. So if you misspell a column name, it will only be at the point when you run that code that you will get an error message. It will also not allow you to do a compile time check that you're perhaps storing the correct data type into a certain attribute as well. Also, you will only get an error once you run this code. If you do use a compiled language, then if you would be using the dataset typed API, then basically this allows you to first utilize a class, which is here simply called T, but where you can say, okay, I do not just know that all of the elements in my data frame are kind of very flexible row objects, where a row is just something that has multiple columns with certain names, and I wait until runtime until you provide me the name, and then I will see whether it exists or give an error otherwise. If you use a compile language, you can say, well, already at the time of compilation, I know that my data set consists of not just row objects, but for instance, something that I call student as a class name. And where I do know for a fact that for every student, which is still a row in that data frame, in that data set, but where I know specifically that they have a name column, that they have an age column, that they have a year of birth column, that they have this column and that column, and already at compile time, the compiler can warn me about accessing incorrect names or using incorrect data types. If you use a language such as Java or Scala, then that's the API that you can utilize. For Python and R users, you will simply use the data frame API instead, because these are not compiled languages and do not perform or do not offer very strong typing constructs. So datasets is even a higher level API. So now a data frame is a data set of row objects, so a collection of generic row objects, a generic untyped object. If you would be using datasets, then you can also represent a collection of strongly typed objects dictated by a class you define in Scala or Java. For Python and R, we don't have that construct. In any case, now that you have this distributed data frame concept, we come again a little bit closer to our ultimate goal, which is then maybe also training machine learning models in a distributed setup. And also Spark knew and saw that this was a use case that people wanted, and hence why MLlib was also implemented as a sub-library in Spark. So MLlib is the collection of, or the implementation of algorithms that then perform you to train machine learning models, also training them on your cluster of machines that you have. So again, you can think of this as a scikit-learn, but running on top of Spark. So hence it has, of course, implementations for different algorithms, supervised and unsupervised, but also to do a bit of featureization, also to do a bit of pre-processing and things like that. Of course, you might be thinking, well, I can always do 2 pandas and then just use scikit-learn, but again, then you're of course doing everything completely locally again, which is kind of against the point that we're trying to make here. MLlib is a pretty early library that was added, and so at first, MLlib came or arrived at a point where the data frame API was not stable yet. So for Spark.mllib, they decided to implement all of the algorithms directly on top of the very low-level RDD representation and construct, which is a bit strange because that means that you're doing something that assumes some sort of structure, as most algorithms do. They assume that you're working with like feature vectors at the end of the day, on top of something that's very unstructured. So that was not yet a very pleasant way of working. Once the data frame and dataset API got stabilized, they decided to then work on the Spark.ml set of packages. And there you do start with something that looks like a Spark data frame, right? So nowadays, if you would be looking at tutorials and they tell you to use Spark.mllib, don't utilize those. They're the low-level implementation. Use Spark.ml instead. Yeah, how this goes with things like this. So yeah, the next step is then that you tell users don't use Spark.mllib anymore. You put them into maintenance mode. You want to deprecate them and kick them out. That never happens, obviously. So it's still in there. But nowadays you would be advised to use Spark.ml because there your input is a Spark data frame rather than just a raw Spark RDD. And then you can look at, okay, what's in there, right? So all your favorite algorithms are implemented. They look very similar as what you would do in scikit-learn, right? You import logistic regression from spark.ml. You load in a data set, which is living somewhere, maybe on your local machine, and then you upload it to the cluster. Or maybe this is something that you read from HDFS or from S3 or whatever. Maybe you want to do something like k-means. So this looks very similar. With that difference that again, this program that we're writing here is just instructing the cluster what it should do, right? So the construction of this k-means solution or the construction of this logistic regression object model that we have is performed on the cluster, lives on the cluster, right? Now you might be wondering, yeah, but okay, we utilize the cluster to then perform distributed training with something like k-means. Knowing how k-means work, you might think, is this so easy to parallelize? Well, yeah, to some extent, right? Remember that for k-means, we need to calculate the centroids for each of the clusters, and then we move the centroids. So perhaps if you have 10 clusters, then we can calculate this separately in parallel for each of the 10 clusters separately where that new centroid should lie. So this is to some extent parallelizable. For something like logistic regression, if you use the closed form solution, not so easy to parallelize, right? Because then you need a full matrix. But if you use something like stochastic gradient descent, and if you would work with something like mini batches, like we saw in the deep learning session, or with what we did with an artificial neural network, yeah, then this might be something that's easily parallelizable, where you can just give different mini batches to the different machines that we have, and we compute a loss, and then we take the average of that, and that's how we, from the gradient of that, we basically update the weights, right? So for most of the algorithms, there do exist ways how you can parallelize them. For some better than for others. Of course, the most elegant algorithm, if you will, or the easiest one perhaps to parallelize would be a random forest. Because if you want to train 100 trees, you can have 100 machines and each of them trains one tree, right? That is basically embarrassingly parallelizable. Even if your data set itself is pretty large, we do bootstrapping anyway. We can make the sample small enough and just build more trees, right? That's exactly what that algorithm offered us. So that's perhaps one of the easiest to parallelize. So MLlib offers parallelized implementations of model supervised, unsupervised model training algorithms. Nice, right? So finally we're there. So hence why Spark was such a big deal, because finally as data scientists we have something where we can finally utilize this cluster of machines that we have purchased, and we can throw out this whole MapReduce thing. So this leads us to some intermediate conclusions. If you look at the state of affairs today, Spark is still being utilized. If not, I wouldn't be giving like an assignment about it. And I'm already kind of at the edge where should we fully switch to just doing something with LLMs instead? But there are still companies, you might go work at a company as a data scientist, and chance is still high that they will utilize Spark, especially if it's like a larger organization with its own in-house team and so on. So hence why it's still necessary to take a look at it. However, the general feel in some ways has changed somewhat, right? If we now contrast where we are at this stage, going or having went through this whole history, we can make some conclusions there. So one conclusion is, okay, Spark has definitely won, been widely adopted, still a main computing platform today. There were others, like Tez, like Mahout. Mahout wanted to implement machine learning implementations on top of MapReduce. That didn't work. Then they changed their mind and they said, okay, we will make implementations on top of Spark, or on top of H2O, on top of Flink. But yeah, Spark itself already offers you an implementation of a random forest. Why would I use the Mahout implementation? No one in their right mind would want to do that, right? So all of these projects have kind of died out. They still exist, which is kind of a drawback of this whole Apache Software Foundation, that if you look in their catalog of projects, they don't give any indication of this is what you should now be using, this is kind of old stuff. Don't look at it anymore. If you visit the website of Apache Mahout and you wouldn't be knowing any better, you read their tagline, you would think, wow, this is great. It sounds very fantastic. They offer everything. So be a bit careful with that. One contender that at some point and still today will also sometimes encounter is that of H2O. And they had a very similar idea at first. They also wanted to offer something that was very much in memory, so not with a lot of disk swapping, fast, and they also wanted to offer machine learning libraries that could be trained in a distributed fashion. At first, they had their own compute paradigm yet again, based on key value pairs and based on heavy forking mechanisms and so on. Then Spark entered the scene, At least they were smart enough to realize, okay, Spark indeed has the better engine with that directed acyclic graph, so we should utilize that, right? We already came up with our better MapReduce, so to speak, but Spark did it better, so let's reduce that. Then Spark also comes with its own machine learning implementations, but not all of them, so maybe we can offer a bit more algorithms. And the way how we have implemented ours are perhaps also a little bit better or more capable than what Spark can offer. So that was their kind of entry point then into the market. Sorry. They called this approach sparkling water, because if you put H2O on top of Spark, you get sparkling water. So yeah, take our algorithms, but okay, use the Spark compute engine to train them in a distributed setup. And one of the things that they were capable to offer that Spark is still less good at is some implementations of more deep learning oriented algorithms, for instance. So that's something. Today, if you want to run deep learning in a distributed setup, you would probably also be looking at other things, because then you go very much to a heavy GPU-oriented workflow. And the way how you distribute learning of deep learning networks over different GPUs looks yet again quite different than how you would think up, or how you would think in terms of offering parallelized implementations of standard ML algorithms. You have more to think about how you have your gradients be computed over your different GPUs and how you spread out those workloads. But okay, at some point, they did pretty well there. And what they still do pretty well is that the algorithms that they do have for tabular learning typically do give you a better performance than what these Spark implementations do. So the implementations are a little bit better. So you could still think of it as, okay, a little bit better of an MLlib. So we did see, we are still seeing companies that are putting H2 on top of Spark for that reason. Another reason is that they have, and this is something that, kudos where kudos are worth, where H2O also heavily has the production setting in mind, where Spark is not very much concerned with that, or, they are concerned with the production setting, but they leave it up to the end users. But questions such as, okay, what happens back when you trained your model, you never saw a missing value for some feature, and now suddenly at production, there is a missing value that appears for a certain feature. Do we have a fallback there? If you don't think of that, yeah, your model will just crash and will refuse to predict. H2O is a little bit better at offering you tweaks and tools to say, okay, then utilize this fallback, or we keep a copy of the training data, and then at inference time, we do kind of an ad hoc imputation, and we raise a warning flag, and maybe that can be a signal that the model should be retrained or should be maintained, but at least we don't completely outright crash. Same for a new categorical level that you did not see during training, and questions such as those. So they were a little bit earlier to kind of think of these kind of MLOps questions, these production-oriented questions that standard Spark does not really concern itself with. Also, they offer like nice UI-oriented workflows to build models and put models into like a model factory, offer an API on top of that. So that's something that they do a little bit better. Code looks like this in R. So H2O also runs on R just for fun in R this time instead of Python. Again, all of this code reads very much alike. Similar thoughts underlying it in that here, this, random forest does not get trained on your local machine. Again, this is something that then gets trained on top of the Spark cluster that you have already running. So MapReduce, not that user-friendly, was not convenient for analytical purposes. Spark reuses some components, but throws out MapReduce. Read the documentation also for the assignment. There, typically, you can find the answers that you would be looking for if you encounter some issues. Directed acyclic graph execution engine, also mentioned. So then later, so Spark was kind of the first one that brought this idea back to the table, not that they invented it. But this is also then what inspired like approaches such as Polars and Dask and Airflow and so on. These kind of local data frame oriented libraries to say, okay, maybe you're not running on a cluster of machines, but the way how you can decompose tasks into such subtasks and then make it, and then perhaps making handling of larger data workloads more efficient, even if you do not have that much memory in your PC, so that we do not need to outright crash or read in the whole data set at once. That is something that was adopted by a lot of these other packages. And maybe today you will not feel the need to install Spark on multiple machines and set up a cluster, but this idea of a DAG and working with something like Polars is something that has gotten quite popular in the data science community. So that powers RDDs, as we saw, programs written interactively. RDDs were a bit hard to learn and use, hence the need for this data frame and dataset API. Okay, then we had MLlib as the next step. MLlib was RDD based, so .ml with implementations of classification, regression, recommender systems. So again, if this part is all that you need, if you only want to do machine learning and a bit of data wrangling and you don't have a cluster, then don't install Spark, right? That should also be a message that you take away. Spark still only makes sense if you do have some distributed setup. If you only have your local laptop, yeah, for the purposes of the assignment to learn how Spark works, fine. But later in life, if you are a data scientist and you just get your laptop and there is no cluster, then your first step will not be, I will install Spark on this thing, right? Obviously not. So in that setting, you would, of course, not utilize it. In a setting where you then will perhaps utilize it and where you're also a bit forced to utilize a distributed setup just based on the nature of the data is once you, very often when you talk about big data, the V there that concerns us the most is that of volume. And yes, that is annoying, but today we have like ways to deal with that, even with standard commodity machine. RAM has also gotten cheap enough. But like maybe another V that is also a bit cumbersome or a bit challenging is that of velocity. Especially real-time data sources, streaming data sources. So also there we could question, okay, how do we handle those? Now, streaming analytics is a name that's heavily overloaded, and Spark there is also a potential solution. But over the years, we have also seen, again, other Apache projects such as Flink and Samza and Kafka and so on popping up as kind of ways to offer lots of interesting solutions, but without much guidance in terms of which one does what and which one brings us closest to the analytics. So streaming real-time analytics, interesting, but there are many projects with similar goals. We also will have to question that what we actually mean with streaming analytics might not be that hard to do, right? And I will tell you why that's the case. So it's important to understand quite well like what we mean or what people mean if they talk about streaming or real-time analytics. If you ask people why, very often you will get answers such as we want to go from one-to-one personalization or one-to-one targeting, or we want to immediately react instead of sending a customer newsletter every end of the month. We want to be immediately react by putting a pop-up in the app as they're using the app based on their real-time behavioral patterns, because yeah, at a Friday evening after you've had like a glass of wine and you're browsing an online shop, you might be more willing to take a certain promotion and press the buy button than if it's a Monday morning and you didn't have your coffee yet, right? So getting these kind of real-time signals is important to be able to do these sort of things, right? To make things more personal, make things more proactive rather than reactive, and those are typically like the notions that you hear. So a lot of it has to do with personalization, a lot of it has to do with becoming proactive, and very often people will also mention like, but the model should be self-learning, right? Also, this is something that you need to be very careful of if you hear like people or consultants talking about self-learning models, because depending on the use case, it might mean different things. There are very little models still today that are truly self-learning, right? Taken to the extreme, self-learning would be that you have a model that also in inference is continuously updating its own parameters. It's continuously updating its own weights. Like if you take like a O4 of OpenAI and you're chatting with the thing, that at that moment it's updating its internal representation. Virtually no model out there does that, right? Even if you chat with ChatGPT, you can make it seem like it's updating itself because it's very good at zero-shot prompt generation, and you can dump in some stuff in the context that you retrieve from a previous conversation with the same user. But if you just look at the weights are trained and stored and used. And maybe next time you do a fine-tuning of that model or your retraining run next month, and then you have different weights, but it's not like a continuous self-learning process at play there. So very often, the way how you have, like, when people talk about self-learning, they either mean we're going to make the retraining cycle of models very short, where we retrain them every week, for instance, or every day at the extreme. Then, yeah, you come close to real-time self-learning, if you will. But also you can think about, is it really necessary that you retrain a model every day, right? Does your environment change that dramatically that you have to retrain a model every day, right? And if so, you end up with like you could call it a second order effect in terms of evaluating such a model, not only now do you need to evaluate like a single training run and being sure that this training run or this model is sufficient to predict well for unseen data coming from the next day, but you actually also have a second level order task where you also need to evaluate whether your retraining approach that you have taken, whether that is sufficiently robust and generalizable enough for the long term, right? It's not because you make the decision to retrain a model every day that you have solved your generalization issue, right? More to the contrary, this is perhaps an indication if someone would tell me, well, yeah, the model after a week, we see that its predictions become worse, so we have decided to just retrain it every day. And did you test out that this approach actually works? Who is to say that maybe there isn't a certain event that occurs 2 weeks from now then, that even if you do retrain every day, still makes that approach invalid, right? So the main reason why consultants like to tell people that models are being retrained so often is because it sounds good to managers, because it makes models sound more fancy, right? And because then they can charge more compute costs on AWS, on Azure, or whatever it is, right? They can charge more development costs as well. But if you would think about perhaps more stable feature sets, maybe your model does not need to be retrained every week, right? Or every day. So a little bit keeping that into account. So that's one way when people talk about self-learning models, what they actually mean. Sometimes what they also mean is that the model is self-learning because it's an ML model, meaning you gave it data, input features with a certain output target, and it learns by itself how to correlate the inputs to the output. Yeah, but that's exactly what every ML model does. Hello, right? So yeah, it self-learned the correlations instead of us coming up with rules. Okay, but that's what we have been doing for 40 years already, so that's also not that impressive. Also, when you hear like news reports on the radio or the media, people will use this term very often, and even like from government users where they have implemented a model that should decide whether someone should get certain benefits from social security, or to decide whether someone has committed some sort of fraud, and some government official comes along to kind of defend that choice, and is it objective, and oh yeah, because we only use these features and not these other features, and let's forget about the ethical questions because some things might be correlated to one another, but also the model is self-learning, right? So even if we do make mistakes, over time they will resolve themselves. Are you sure of that? Right? What do you mean with self-learning? Is there the model doesn't retrain itself, right? It doesn't decide itself to evaluate itself and retrain itself. So all of that aside, what now has to do then with streaming analytics? Well, to do that, we need to differentiate between what we actually mean with what is the streaming aspect. For sure, you might be willing or you might be wanting to use certain data sources for the construction of your model, even although that training of that model is just a one-off, a one-time thing, but where you're wanting to use certain data sources that arrive as a continuous stream of events or messages or data, like tweets, and you can connect to the Twitter API, and that comes in as a fire hose of data, so your data source emits events or instances or whatever. There, of course, the question will be more infrastructure related. Well, at the very basic level, that means that I need to be able to monitor that data source and construct a sufficiently large historical set of data, basically convert this streaming data source into a static tabular one that I can then use to train my model with, right? But it's more about like monitoring of it, plumbing of it, and so on. And the more extreme case, that's the most common case. A bit more extreme would be, no, my model also really needs to perform streaming training. I'm really looking for something where my model does update its own parameters as data continues to come in or as it is being used. You would be hard-pressed to find real online implementations of models that really do so. Or even in the space of deep learning, people have presented methods where weights of a neural network are being updated as it's being used. It's never really implemented in practice. And at a very extreme case, even if you have an algorithm that cannot do this, right? Or even if you read papers about some kind of, even a k-means that's capable to update its own kind of cluster solution as new elements come in, very often it boils down to two things. You just make the retraining cycle shorter, and you just say, well, every day retrain yourself on the past 2 weeks, right? And then you basically have a continuously being retrained version and continuously being trained version of that model. and probably with another loss component that you put in there as well, where you say that the parameters of the new version of the model that you built should not differ too much from the parameters of the previous version of the model that you had. So that you also have like some kind of flow direction in there as well. And then you have your streaming training. Very rarely seen in practice, right? Even though it sometimes sounds like this is certainly not a common meaning under the term. What is also more common is that you say, well, not only do I need to train my model on something that comes in as a stream of data, but also at prediction time, when I'm using my model to do inference, it needs to be connected to again, a stream of instances or events. I have events that come in from users utilizing the shopping app, for instance, clicks that they're making and scrolls that they're doing and likes on TikTok and so on. And at every event that comes in, the model needs to be able to give a signal saying, now is the right time to show them this particular advertisement, yes or no, or which advertisement should we show them next, right? But then you're talking about usage of your model. Then you're talking about deployment of that model, operationalization of that model. It just needs to be able to be called fast enough, right? You're back to kind of the productionization context. So if you can keep a historical set of data, if you're capable to handle this, you don't need streaming training. And is this even hard to do? Yeah, maybe, of course, it's an infrastructure question, but like from an analytical point of view, maybe not that much. And here, well, how many events do you have coming in? Are you TikTok? Are you Uber? Do you have 10,000 events per second, 100,000 events per second? Again, this is an operationalization question. Just put your model in an API, put it on Kubeflow or Kubernetes or Docker, Swarm, and just spawn 100 machines if you need 100 machines with a load balancer on top of it, and just have it answer or spawn out predictions as events come in. Some examples. Netflix has about 9 million events per second at peak. LinkedIn, 500 billion events per day, and so on and so on. Think about WhatsApp, think about Uber, but do you really compare to this, yes or no? As a bunch of interesting examples, in the setting of streaming training or continuously updating models, I only really saw two examples in practice where companies try to set something up like this. In the case of Netflix, they have their recommender system, which is not being continuously retrained based on your actions. It's way too heavy and large for that, right? And it also needs to be able to serve multiple users. It's not personalized towards, they don't have a model per user, basically. So they train that and retrain that from time to time, especially if new movies come in, they need to be incorporated in the recommender system and so on, and perhaps it's a good idea then to retrain. So they do that from time to time, and they utilize that when you open up the Netflix page to kind of give you, well, these are the next 5 things that would probably be interesting for you to watch. Does that mean that you cannot use any real-time, personalized aspects in such a model? No, of course not. It depends on the features that you utilize to train that model, right? If you collect a sufficiently historical set of data, put the time of the day as a feature. Put information about the user as a feature, right? Even the way or which device that they're using, you can put that in as a feature, right? It's not because you only trained your model last month ago that in terms of features that it utilizes, you couldn't stick any real-time information in there. That's just a choice of which features that you utilize. Second, what they do on top as well is on top of the base predictions that model gives you, you could still then scale up or down those predictions or re-rank the recommendations a little bit, perhaps based on the latest real-time information that you have. So then you're taking a bit of a rule-based approach or a little bit of a filtering-based approach or a little bit of a re-ranking-based approach on top of baseline predictions that your model already gives you. That is typically more driven by rule-based systems, gut feeling-based systems, maybe very small models, which can maybe be local to users. But in the case of Netflix, you have way too many users to have a local model per user. But then you can make some adjustments at least to those baseline predictions that the model gives you. That's also still an opportunity. And that's what Netflix, in fact, is doing. Another interesting, but of course they have all the knowledge about this, another company that has, and it's also in the space of recommender systems, that has published results where they do say that they are really very close to a continuous retraining of the underlying recommender system model, and you can read papers, they have been published and quite clever stuff in there. But this is from ByteDance, right? So the company behind TikTok. So they also have a lot of work into models which are very continuously updated as well. So they also have a lot of clever systems as well. But in the majority of use cases, and it's mainly in the space of recommender systems where you see this, but for many other cases, you can just use a once-trained model. If you think carefully about the features that you put in there, you can still utilize it in a very proactive, very fast, reactive manner as well. If we then look at the data, well, specifically, if you have a source of data, well, before we always worked with like what we consider we have finite data. We have just a tabular data set that we load in. Well, if you work with streaming data, then you basically assume that the data has no end. As long as you continue monitoring the data, you will get more and more events, more and more tweets, more and more instances that come in. So in this case, you basically need to kind of say, okay, now my data has become infinite. As long as I continue listening, my data will come in. And then there is a mechanism or a difference in terms of how you process that data. So in terms of the engine that you utilize to work with that data can be streaming as well, or can be batch. And combinations of both are possible, right? You might have a finite data set, but you can still pretend that you're crunching this through some kind of streaming processor. If this data is ordered based on time, you can basically replay and simulate those events as they come in. Okay, it will not be infinite, but it will be long enough to at least process them in based on a streamed processor. Similarly, for infinite data, well, nothing is stopping you from taking the point of view where you say, well, every week or so, I will monitor this data and I will store it somewhere. But then every week, I just grab the data set that I have there, that I have collected over the past week, and that is then just a finite static data set that I could utilize with whatever that we have been using. Doesn't need to be a streaming engine. You can load that in into Spark or into scikit-learn. You can do a retraining of your model then, and then you're also done. Now there is one thing, of course, that is a little bit more tricky if you work with like real infinite streaming data, is that, yeah, you work over the network, so typically it's possible that events, they arrive late, for instance. And how do you order events? Is it the time of creation of the event, when the user pressed a certain button in the app or did something, or is it the time when that event arrived in your system, right? What do you do if an event arrives too late? Do you still try to incorporate it in some way, or do you decide to ignore it? If you want to perform some sort of aggregation function, and you say, okay, for each genre of book, give me the average number of pages. Well, now if I tell you, yeah, but books continue to arrive every day, you can't wait until the end of time to create that aggregation. So probably you will have to define some sort of window then of your aggregation that gets continuously updated as well. So those are things that do make infinite data a little bit harder, especially for aggregation operations. With finite data, the result of an aggregation is a singular thing that happens once. With infinite data, the result of an aggregation is probably itself a stream that continuously gets updated over time, and where you only look back every so many rows or so. So that's something that does change if you would work with a streaming data set. And then how you perform this windowing operation, either you slide based on time or based on count of instances, or you perform some sort of hopping approach. Well, you do need to make, or you do need to add in a windowing mechanism in the way how you express your aggregation. So you will not be able to just do a dot group by anymore and see the result. The result of a group by will now require both defining a window, and also the result itself will be a stream of a number that continuously gets updated over time. So okay, let's say we have a streaming engine that can provide us this. Do we then still need an online algorithm? Well, like I said, perhaps not, right? It's hard to find them. And in most cases, the question is more, okay, we want to utilize streaming data, so we'll need to store it and access the history. Probably or likely, I have events, and I want to take my trained model and have it perform predictions in a very speedy context where events arrive very rapidly, and I need to be able to react to them quickly and send something back to the app, and the app needs to be able to show something based on that prediction. But still, the training can be done offline in most cases, perhaps very often or very periodically retrained, but still the training can be done offline. And then the model can be deployed in a streaming setup. And depending on your needs, you can decide to retrain how often that you need to. But again, it's not because you have a very high velocity data set that automatically should mean that you should also retrain your model every hour of the day, right? That kind of more depends on the volatility of your environment and how necessary that really is, and also which features that you incorporated. So again, you can have very reactive features or very up-to-date feature information. Doesn't mean that your model itself needs to be up-to-date in terms of when was the last time that you trained it, right? If customers today still behave the same way as they did last week at 11 o'clock at night and at 1 a.m. at night and 7 a.m. in the morning, right? Well, then you don't need to retrain your model. You just need to be able to tell your model that currently it's 7 a.m., right? So in terms of technology that's available, I like to use kind of this overview because it shows like a nice separation of concerns. For us, we're mainly looking then for something where we can say, okay, how do we then connect to a streaming data source? And you can already see Spark orients itself in the processors, and then perhaps includes such sources in the construction of our models. And what makes it easy for us that we take a trained model and also deploy it on top of something that's streamed data by nature. For us, it will be mainly the processing engines, as you see here. The others are also important, but again, more from an infrastructure point of view, rather than really an analytical point of view. And the ones that are afterwards, these are more for like business intelligence or indexing with text data and so on, and already a bit higher level than what we are looking for. So as some examples, so we are on a quest, let's say, to find something that can help us with our analytics, but now in a streaming setting. So basically our question is, okay, assume a data frame, but now the data frame is infinite. So every second, this thing grows and becomes longer and longer with new elements that comes in. Is there something where I can still express all the operations that I want to do on this data frame and perhaps the construction of a model, and now not having to work with a finite static data frame anymore, but something that I've plugged in to a streaming source of instances instead? What can help me to do that? Well, event collectors, the first block here on this slide, as they suggest, they will not really help us with that because they gather, they collect, they centralize events. So some Apache projects that do this, Flume and Nifi, but very often, like Flume is something that stemmed from the question, you have a cluster of 100 machines and you have Hadoop running on top of that with its HDFS and MapReduce and Ambari and Zookeeper and this and that and this, and all these machines are generating log files. Is there a way to centralize all of these log files together? Yeah, let's invent something else. We call that Apache Flume. And if you think about the question of centralizing log files to a central location, that's probably a question that you don't only have for log files, but if you think of any sort of message or event that arises from some source and that you want to centralize somewhere, probably this thing is also something that you can help you with that. So as an event collector, this is something that can help you there. Yeah, okay, fine, but analytically, not really, right? This is just kind of a centralization thing, so not that helpful. Event brokers then go a step further and say, well, okay, you don't just want to collect events and bring them to a central location, but probably your infrastructure, you have a complicated set of networking, or maybe you are like an app provider, something like an Uber, and these apps are sending you events and you need to route them in your data center in the right ways, and apps can subscribe to certain messages or it can send you certain types of messages, and yeah, you just need a way to deal with this kind of overload of events and information that comes in a way that can scale, where you can handle 10,000 events per second, where you can bring them to the right sinks to store them, perhaps because you want to utilize them later, or you need to maybe queue something that needs to happen and so on. Again, you're still very close to the infrastructure side of things. So then typically this also gets called message-oriented middleware. And very often here you see projects which have MQ in the name, standing for message queue. So these are projects that are able to take in a whole slew of messages that come in and are able to react to those messages in some way. And in some way then depending on what the app is that you're building or what it is that you want to build, right? As an example, perhaps you're trying to build the next YouTube, for instance, and you have like 100,000 users using your website at once, and they're all uploading videos. And typically what you need to do after a user has uploaded a video, you need to convert that uploaded video into different formats so that both Android machines and iOS machines and this web browser and that web browser can play the appropriate format. Some browsers support MP4, some do not, so you need to do a transcoding step from the uploaded format to different formats. Yeah, it would not be a good idea that you have this happen automatically or immediately at the machine that the user uploaded the video to. If you only have like 100 machines and you have 10,000 users, that would probably not work. So if you're YouTube, what you do instead, you first have the user upload their video file, you store that somewhere, and then you spawn an event saying, well, this is a task that's waiting. You put that in the queue. Right, so that machine sends out a message saying, the user has just uploaded this video. I've put it there on S3 or on HDFS. someone, if you're ready, please get busy with converting this video into the different formats. So you have a whole queue of waiting tasks, and then you have a bunch of machines that are continuously running and taking out jobs from that queue and working on transcoding that video into different formats. Also the reason why if you upload something to YouTube that you get a message saying, well, wait a bit before we are finished converting your video into the HD and the standard definition and so on, right? So again, you're talking more about like infrastructure, about setting up routing and so on. So helpful there for sure, but if you think about our infinite data frame, obviously not so much. It's only with the event processors that we really come to that use case of, yeah, I really am looking for these kind of data frame-oriented tasks again, and these machine learning-oriented tasks again. And Spark itself has actually a solution for this. The first one being simply called Spark Streaming. And again, this is based on the lower level RDD abstraction. And then later on they said, yeah, okay, but couldn't we also think of an infinite data frame? Because we have this data frame mechanism. Well, let's call this Spark Structured Streaming. So the name structured is pretty important here. These are two different things, Spark Streaming and Spark Structured Streaming. And they do not take the most aggressive approach because their main kind of angle of attack was, well, let's do it in a way where users can utilize all of the things that they knew how to do with a single RDD already, or in the case of structured streaming, all of the things that users already knew how to do with a single data frame, and it should be just as easy to express or perform these operations if this RDD would be never ending, or if this data frame would be never ending and connected to a fire hose of events that come in. So that is the approach that they took. And the way how they do so is, well, what we're going to do, you're going to connect to an input data stream that's never going to end. But every so often, we're going to collect all the elements that we saw between now and 5 seconds from now, and we're going to stick all of these in an RDD, and then you can just say what you want to do with that RDD. And 5 seconds later, we'll have a new RDD, but you have expressed the operation, so we'll also execute the operations on that RDD. So every RDD itself is a list of elements, and now we're just going to provide such an RDD over time every n seconds. And once we know how to do it on a single RDD, we also know what to do 5 seconds later, 5 seconds later, 5 seconds later. So also the output is going to be batches of processed data. Spark calls this internally a D stream, a discretized stream. So a D stream is a list, or a continuously arriving batch of data, a batch of data being an RDD. So a D stream is a sequence of RDDs, and an RDD itself is a list of elements, in this case, the elements that were collected between now and 10 seconds from now, or 5 seconds from now. And then you just tell me what you want to do with a single RDD, and I know what I have to do for the next RDD, for the next RDD, and for the next RDD. The only thing that's probably going to differ is that if you say something like, I want to aggregate something, well, now I will not wait until I have all the RDDs because they will never end. So there, that is where that windowing will have to come in. But things such as, well, if you tell me how to count words for one RDD, well, now I could just be monitoring lines of text that come in, right? And the first batch is going to be all the lines between now and 10 seconds ago. Well, I can give you an output. And then the next 10 seconds, I can give you an output. The next 10 seconds, I can give you an output. So also, just as if you would have expressed an operation on a single RDD, you can do the same thing on a D stream. The output is itself going to be a stream as well, right? But maybe every 10 seconds you say, well, now save this thing to a text file somewhere for every 10 seconds, or react in some way, or send a message in some way, or take a load-up model and make a prediction in some way and send it back through the API. So these are things that are then relatively easy to express. If you know how to do it for a static RDD, you know how to do it on a stream of RDDs. And that's basically what the examples for assignment 3 have also been showing you. So you first define everything that you want to do, and then you basically say, okay, start processing the stream. And then you lose control, obviously, because then the thing gets going and never stops running, basically, right? So that's the D-stream abstraction. With the problem, of course, here being is that all these RDDs that we process, that they're still RDDs. So, okay, that's low level. Can't we bring it now to the level of a data frame? And hence, if you put the word structured into the name, this is what this will give you. The only other thing that changes, like I said, is okay, you will not be able to reduce by key anymore because this thing never ends coming. So you never know when you run out of values for a certain key. So you need the end window there where you say, okay, between the window length is the duration of the window. In this example, the duration is 3 steps, right? So you always look 3 steps back to make your window, and the sliding interval, which is the number of steps that you slide your window by. So now your output stream is you do not get an output batch for every input batch that you receive because you're windowing them. Now you get an output batch for every 2 steps that you take. But still your output is a D stream, is a stream as well. So only the way how you need to do aggregations change. You can still also join streams together if you know how to join 2 RDDs together. The same thing can happen every 10 seconds as well. So not a lot changes, which is one of the core benefits of Spark streaming, is that if you know how to do things on a standard RDD, you know how to do them on a D stream as well. Yeah, RDDs, like I said, do we have the same thing for data frames? Well, yeah, sure. First of all, can you connect this thing to MLlib? Well, yeah, of course. The most common use case is that you utilize Spark streaming to save a bunch of data. Then you train your model off-site or offline. But then you have another stream where basically in the code of your stream, like we saw here, you load in your model and you just have it predict on the incoming elements as well. So it's pretty easy to set it up. Now, structured streaming then is the mechanism where, okay, but a stream of RDDs, yeah, but we want to use not MLlib, but Spark.ml. So what about the data frame? How do you express a data frame that comes from a stream of instances? Well, not that difficult. Basically, then you assume that over time, your data frame will grow and grow and grow and grow. Of course, not infinitely so, because we don't want to keep this never-ending thing in memory. At some point, this will crash. So probably also here, this will grow at the bottom side, but over time, as elements become too old, we'll probably kick them out as well. That's going to be the idea there. But then every operation that we express at every 10 seconds again, if I say, well, here is the data frame as it is right now, and I want to select these 2 columns and add them together and then do this with them, also every 10 seconds I can construct an output version of that data frame as well. So again, that mechanism of working in batches over time does not change here either. So input feeds me data at every time step, and then also my result hence gets updated every time step. So now very similar, you still have a trigger every second or so, or every 10 seconds, except that now you're working over a data frame construct rather than an RDD construct. It tries to be smart in not keeping the whole table around, so it also looks at what it is that you want to do with this data frame. Again, if you say, I only want to keep a count of data that gets updated over time, right? Then we do not need to keep all of the data around to update that count. Once we have the count up until now, I can basically throw away all the data. If then in the next time frame I get 10 extra elements, I just need those 10 extra elements, update my count, I can throw it away again. So we can be smart in terms of how much data we need to keep around. So we only keep around the minimal intermediate state that we need to update this running result. Of course, in an extreme case, you might be willing to keep like your complete data frame around, in which case, yeah, at some point you will have to have, or you will need to throw all the data away, otherwise your machines at some point will crash, obviously. Sliding events, very similar with additional mechanisms, and that's a bit of a detail, but just to know that Spark provides this. Like, what do you do if an event arrives late, for instance? Do you still include it in your aggregated window that you had before, or do you make a new row and you include it now? So how do you deal, or how do you want to deal with events that arrive too late, for instance? Do you then include them in the next update, or do you still update a previous result? How do you want to handle that? So late data that was generated here, but it only arrived in here. Do you want to increment the previous count, or do you not want to do that? And you just ignore the event if it arrives too late. So it also offers mechanisms to tune those sorts of operations if you work with structured streaming, which is something additional that normal Spark streaming does not offer you. Structured streaming also provides you mechanisms to deal with this. Less important for the assignment, but obviously if you're thinking about like setting up more complicated pipelines, then these sorts of things, being able to manipulate this is of course handy to have. In terms of code, you work with Spark.SQL, just like with the data frames. Also the Spark session for streaming data lives in here. but again, you're working on the level of data frames. So this is still quite popular. There are other processors as well, which came and went, including Storm and Samza and Apex and Ignite and Beam and so on. So like I said, Apache can't stop thinking of new projects. The one in here, which is maybe the most interesting one, is Flink, which does a lot of similar things as what Spark does. Maybe a little bit more stream native than Spark is. Spark decided to make it to keep it relatively simple. Flink tries to go a bit further, and instead of mini batching data, is also a bit better in true real-time contexts. It got traction, especially for use cases where this mini batching is not sufficient, and you want to go even further than this, or you really have a whole lot of events that you need to be able to handle. Was adopted by companies like Huawei, Tencent, Lyft. Here or in common organizations did not really find that much traction. Probably if you, or also the reason being that if you went through Hadoop and H2O and Python and scikit-learn and this and that, then you arrive at Spark and probably you're not really in the mood to really change to a complete new compute platform afterwards anymore. And then if you go further, yeah, these indexers, these are typically more concerned with dashboarding and business intelligence, not so much in terms of predictive modeling or data wrangling. I mean, you can find presentations where IBM or some other company shows you, we have built like a real-time map of container ships as they're moving throughout the world, and a black background and dots, and look, this is real AI and intelligence. Yeah, no, you have a real-time dashboard, super cool, but you're not really building a predictive model there or doing AI. Of course, can be handy, and also for dashboards and reports, the more real-time that they are, the better, obviously. But again, this is some sort of other offering, and again, boils down more to, do you have streaming data sources available, and can you just plug into them and then parse the data that comes out? So again, time for a bit of conclusions. Yeah, like I already mentioned, this Apache family, they have a lot of family members in any case. They all have common kind of underlying ideas. They all, of course, are open source first. They like Java a lot. They feel very enterprisey. Some of them depend on others. But again, some seem very new but unfinished. Some might be more old or they're useless, so hard to make sense of this all. And you can find even websites where they list like all the Apache projects that are out there. And you can see that it's also way more than the ones that we have been just discussing. So like the list is endless of like Apache projects, and yeah, good luck if you're a company that has installed all of these. You wouldn't know where to begin, right? So again, don't adopt all of these. First, think about your problem before you go hunting for a solution. The slide at the bottom kind of says, okay, you can start with Hadoop, and then you went to Spark, and you added H2O on top of that, and then at some point Kafka was very popular, but not anymore, and then maybe now you're thinking about switching to Flink. So okay, what is the current trend? And maybe the current trend is a move backwards away from these kind of distributed platforms, also for many organizations. Again, if you're not like a very large organization, good luck getting started with all of this as well, obviously. There's some more recent examples just to show you like, okay, now what is this more or less than something else? Apache Druid is a newer one. A high-performance real-time analytics database that delivers sub-second queries on streaming and batch data at scale and under load. Yeah, okay. What is this now, less or more than what I had with Spark? I already have Snowflake. Is this then better, or is it not better? Who knows, right? Apache Feldera, a fast query engine with the unmatched ability to evaluate arbitrary SQL programs incrementally over any number of live and historical data sources, millions of events per second, scale larger than memory data even on your laptop. Okay, nice, yeah, but again, it's kind of SQL on streaming and batch data. So they all kind of reinvent the wheel. You have Hive tables and Parquet data and Avro data. Forget about that. Now we have Iceberg, which is a new open table format for analytical data sets. So don't get too swayed by these projects. Of course, the fundamentals and the ideas underlyingly are very often the same, but people end up reinventing the wheel many times over if you follow these kind of projects. And this is only from like the open source perspective. If you then take like the consulting perspective, and you look at these like at these magic quadrants of Gartner and so on with the leaders and what is it? Yeah, of course this is based on companies that pay to be in that magic quadrant, but very often they utilize underlying open source systems anyway or libraries. So also there, don't be too swayed by kind of new developments that you see. What are the patterns that we see nowadays? Well, a couple of them. One pattern is that the hype around big data is luckily over. For storage and querying, we're kind of like at the stage where we just take the best of breed, which is either like something like a DuckDB or a cloud-based solution like a Snowflake. For analytics, multiple patterns, still very heavily notebook-driven in most cases, where people decide to go pure Python, notebook, VN for UV or Poetry or something like that, and in many cases also in the cloud, using an Amazon SageMaker or an Azure Machine Learning Studio or something like that, which is basically just a hosted Jupyter environment with Python environments. Or you do it yourself and you deploy your models as an API using Fast API, and you take more the microservice approach, or you use something like Docker or Terraform, or you do everything on GitHub with GitHub Actions. That's also a common pattern. Sometimes you implement or you utilize heavily local DAG-based data crunchers like Pandas 2.0 or Polars or DuckDB or Ray or Airflow or whatever. Others say, well, forget about all of this. We go for a pure deep learning oriented approach, and we don't use scikit-learn or Spark or whatever. We do everything using TensorFlow. And even if you have tabular data, we use TensorFlow, and you build like some ANN on top of that, and that's the way how we do it. Or we do everything using a PyTorch-based environment, or sometimes combinations of these. And others say, well, we have Spark running. We are more an enterprise environment, more larger organization, so we still use Spark with or without H2O, with or without Kafka. There's also still a pattern that you see today. Now, of course, focus on what matters. So these are some screenshots. If you would be thinking, oh, wow, these large organizations, they are really getting the most out of Spark. Well, no, not always. When Twitter's source code got made public and people could take a look at which were the Scala programs using Spark that were actually written, mainly it was like distributed storage, and then expressing very much like, even if you think about how should tweets be boosted and be shown and be ranked, you would be surprised how much of this was still kind of hand-coded rule-based stuff. Not with like 100 predictive models running behind it, but like manually kind of up-boosting and down-boosting users based on the number of mutes that you got, the number of blocks that you got. So don't be surprised sometimes that people also do A/B testing and try to figure out hand-rolled rules where there is no real data machine learning driven learning, but it's really people thinking of rules that they then implement using Spark, using a Scala program to kind of create some kind of score without touching this ML stuff or MLlib stuff at all. So that's also something that you can observe, and is also not that uncommon when working with Spark in these organizations. So be a bit careful, like not everybody needs distributed systems, as these quotes also state. There is also very famous paper, Scalability, but at what cost? That definitely proves that if you're not working at the scale when these distributed systems are a necessity, that it does not make sense to use these systems, because you will end up spending more than if you would have chosen a more leaner, more agile setup instead, right? So definitely not use this as your first solution out there. And I already mentioned this, like these magic quadrants. It's always fun. This is an older comparison, but you can do it for 2025 and 2024. Put two versions over 2 years of these kind of quadrants next to each other, and they have completely moved and changed. So yeah, you can get advice now, but basically they're saying that next year it's already outdated. Also, this is based on who pays to be in there. And if you actually look at these companies, there are company names in here, not library names or technology names, right? These companies adopt all the underlying technologies anyway, so if you really want to know what's coming, it's better to look at technologies rather than at company names. How do you do that? Well, steal from the best. Take a look at blogs from engineering teams from companies that have suffered through this before and that are really encountering the issues that companies dealing with large data sets and companies that do a lot of machine learning face. Companies like Spotify and GitHub and Facebook and Netflix and so on. Not that you should become the same company, and certainly not in, and the things that you sell might be completely different, but if you are doing some sort of machine learning, very often these companies are the first to encounter some kind of hurdle where they see, well, for this there are no turnkey solutions yet. This is something that was an issue for us, so here is how we solve this. And a lot of open source projects and libraries and technologies that appear over time kind of come from these kind of initial hurdles that people face. Google File System was such a thing, but also today, if you look at machine learning ops, for instance, was the same thing. Oh, we have so many models running in production, but we can't monitor them. When is it time to retrain them? No, scikit-learn doesn't tell you, right? So how do we set this up so that we can get some more management out of this? Today with AI, yeah, we want to use LLMs, but how do you set up guardrails? How do you do that? We want to set up a retrieval augmented generation. How do you set up the right database for that? Should we use it this way or we should do it this way? My data scientists, they like to use notebooks, but my IT people hate this. How do I put notebooks into production? And how do I get some more governance on top of that? So all of these things are always the result of like initial issues that people face there, right? And perhaps the most important takeaway is obviously, and this has kind of been the message, is that start with the analytics and with the insights. You don't have to be a large engineering-driven company by all means, and you will also likely not have the capacity later. Also be a bit honest, do you really have big data? Managers like to boast to each other that they are spending like millions on AWS and I'm more important than you, but what do you actually do with it? Even with small data sets, you can get great insights, and sometimes the data sets that people do not immediately think of, and those are typically the ones that are not yet in some kind of centralized cloud platform, but are like living at the edge of the organization, might be more interesting to utilize than just a dump which gets restuffed and re-imported over and over again from one technology to another. Like what was first living in a data warehouse, your typical customer features, that gets then transported into Hive tables, and then you dump it on top of S3, and then you dump it into Flink, and then somewhere else. At the end of the day, you're just reusing the same feature sets anyway. You're just using different mechanisms to write what's, at the end of the day, SQL queries, right? And also think about people and processes like governance, deployment, maintenance, monitoring, and most of all, the business question underlying it. So don't forget that if you think, or if you'd ever be working with like heavy technology facing things, or you would be talking with architects. Architects always dream of architecture, but typically for IT, contrary to engineers and architects in the real life, they really have to finish the building or the bridge, and it shouldn't collapse. IT architects have the liberty to leave a bridge half finished and then go look for a newer, fancier bridge that they can build, right? So be a bit wary of that as well, especially as an analyst or as a data scientist that would be working with these technologies. Good. That's it for today. Like I said, next week we will look at text mining, and also in the course of this week you will receive the data sets for the last assignment with some instructions as well. See you next week.